In the vast expanse of the universe, where countless stars twinkle and countless worlds spin in elegant harmony, there exist objects unlike the familiar planets we know, those bound to blaze in the warm glow of a sun. Instead, these peculiar wanderers roam the infinite cosmic wilderness alone, untethered to any star, drifting silently through the void. They are known as rogue planets, mysterious travelers of the galaxy that illuminate a different chapter in the story of planetary existence. Imagine the night sky, vast and deep, where every familiar point of light is a star, perhaps thousands of light years away. Orbiting many of these stars are planets, worlds that, like Earth, thrive on their intimate dance with the sun. Our own solar system, with its 8 planets circling the sun, stands as a testament to such celestial order. Yet, out in the dark, reaches far beyond the luminous warmth, rogue planets traverse the galaxy, obdurate and solitary, without a sun to pit them against the dark. The concept of a planet has often been intertwined with the idea of a star's family, where planets reside in the protective sphere of their star's gravity, receiving light and warmth, clinging in these orbital embraces for billions of years. But rogue planets challenge this notion, drawing us to question, what if a planet has no star? What if its path is not dictated by the gentle gravity of a sun, but by the chaotic waves of the galaxy's gravitational tides? Rogue planets are planetary mass objects that wander through interstellar space, unbound from any star's gravitational influence. They are cosmic nomads, drifting through darkness, carrying no sunlight upon which life as we know it depends. Yet, their existence hints at the complexities and dynamism of planetary system formation and evolution. These celestial vagabonds intrigue astronomers not merely for their unusual status, but for what they reveal about the nature of planetary formation and the life cycle of solar systems. How did they come to be unmoored from their parent stars? Are they planets ejected violently by gravitational tugs within dense star clusters, or were some born directly in interstellar space, never anchored to a star at all? To understand their place in the universe, it helps to picture the galaxy as a vast ocean, with stars as islands scattered across it. Most planets are tethered to these islands, circling their suns like small boats bound by strings. Rogue planets, however, are akin to castaways, without anchors, drifting freely over the cosmic seas. The sheer possibility of such lonely travelers expands our appreciation of the galaxy's complexity. It tells us that planetary systems are not closed, stable configurations, but dynamic and sometimes turbulent arenas where planets can be born, wander, and wander again. While their dark and solitary nature might suggest insignificance, rogue planets potentially outnumber stars in our galaxy. This staggering prospect opens a new frontier in astronomy, the study of objects that are invisible in reflected starlight, detectable only through subtle gravitational signatures or faint emissions from internal heat. In terms of composition and characteristics, rogue planets may share traits with the familiar planets of our solar system, ranging from rocky terrestrial worlds to gas giants far exceeding Jupiter in size. Some might still retain atmospheres heated by residual internal energy or radioactive decay, providing little pockets of warmth amidst the frigid darkness. Others might be frozen solid, lonely, and inert, carrying the cold stamp of interstellar space on their surfaces. Moreover, rogue planets invite us to imagine environments profoundly different from those found around stars. Without solar radiation, their climates, if such a word applies, depend entirely on internal heat or tidal interactions, perhaps fostering subsurface oceans cloaked beneath thick, frozen crusts, potentially viable habitats for microbial life in a universe otherwise harsh and cold. Their isolated journeys also raise fascinating questions about interstellar interactions. Could rogue planets, wandering close to other star systems, perturb or even collide with established planetary arrangements? Could they serve as cosmic messengers, carrying the ingredients or seeds of life across the vast separations between star systems? The discovery and study of rogue planets represent a humbling reminder of the universe's boundless variety and the incomplete picture we have of the cosmos. They underscore a fundamental truth. The galaxy is not a static backdrop, but a dynamic theater, full of surprises and mysteries, beckoning us to explore the unknown. As we embark on this exploration, understanding rogue planets offers a fresh perspective on planetary origins, stellar dynamics, and perhaps even the possibilities for life beyond the comforting light of a star. The silent, solitary wanderers of the cosmic wilderness challenge both our scientific curiosity and our imaginations, urging us to contemplate the universe beyond familiar light and warmth, a cosmos richer, stranger, and far more enigmatic than once imagined. In the chapters that follow, we will journey through the ancient tales and scientific revelations that have shaped our understanding of these enigmatic worlds. We will delve into how these solitary planets escape detection, the methods used by astronomers to unveil their secrets, and what they might mean for our understanding of life and the universe at large. From their mysterious origins to their place in the cosmic dance, rogue planets stand as witnesses to the wild, untamed spirit of the galaxy, a poignant reminder that the universe is full of cosmic stories waiting silently in the dark, eager to be told. Long before the advent of telescopes and the precise instruments of modern astronomy, ancient civilizations looked up at the night sky filled with wonder and curiosity. The celestial canvas above was a tapestry of lights, fixed stars that seemed to hold steady through the ages, and wandering points of light that shifted their positions from night to night. These moving objects were among the earliest cosmic riddles, inspiring myths, legends, and early attempts at scientific understanding that would lay the foundation for our later grasp of the universe. To grasp how ancient cultures perceived objects reminiscent of today's rogue planets, we must start with their observations of what they called wandering stars, an epithet that in many languages eventually became the term planet itself. Deriving from the Greek word planets, meaning wanderer, planets were recognized as distinct from the fixed stars because of their erratic paths across the sky. Ancient astronomers in Mesopotamia, Egypt, Greece, India, and China meticulously tracked the motions of these objects, noting their unique behavior among the stars. These wanderers included Mercury, Venus, Mars, Jupiter, and Saturn, visible to the naked eye and the planets that shaped early astronomy and mythology. Their wandering was sometimes seen as ominous, sometimes as divine, interpreted through stories that fused observation with spirituality. Yet, despite the precision of their records, the ancients were unaware of the vast distances involved, and certainly unaware of starless worlds drifting through space. However, the night sky held even more mysterious shadows, intriguing notions of dark or hidden planets. Some texts and oral traditions hinted at invisible worlds or traveling dark bodies, objects that could neither be seen in reflected sunlight nor easily tracked, but sensed through their influence. Though none explicitly identified rogue planets by the modern definition, the idea of solitary cosmic travelers found a place in folklore and early cosmologies. The Babylonians, among the earliest stargazers to develop comprehensive celestial catalogs, meticulously recorded the movements of planets, but also expressed an understanding of celestial cycles and irregularities that suggested to them deeper mysteries beyond the visible. Similarly, the ancient Indian astronomer Aryabhata and later Varahamihira advanced complex models of planetary motion that accounted for anomalies observed in the skies, concepts critical for the refinement of planetary science in their era. Though these ideas remained firmly tethered to objects orbiting the Sun or Earth, they reflect an evolving curiosity that might someday be extended to comprehend rogue worlds. In ancient Greek thought, philosophers grappled with the nature of the heavens, formulating theories about celestial spheres and the perfect circular motions of planets and stars. The works of Ptolemy consolidated a geocentric model with epicycles explaining planetary wanderings. But the notion of planets unbound to any central body was absent. Still, the Greeks, through their philosophical reasoning, entertained the idea of multiple worlds and cosmic plurality. Some thinkers like Epicurus speculated about infinite worlds, many like our own, some very different, and perhaps unattached to stars as we understand them. Farther east, Chinese astronomers documented transient celestial objects such as comets and novae, but recognized planets mainly as the 5 wandering lights known to them. Their celestial science was rooted in careful record-keeping, essential for the imperial calendar and astrological purposes. Ancient Chinese texts sometimes spoke of dark stars or periods when celestial objects vanished or appeared suddenly, perhaps hinting toward the knowledge that not all cosmic bodies shine consistently or predictably. Yet no clear reference exists to free-floating planets. In the Middle Ages, European astronomy inherited and refined much classical knowledge, but the cosmos largely remained a star-centered arena. It wasn't until the Renaissance and the dawn of telescopic observation that questions about the vastness of space and the nature of planets took on a new dimension. Even so, the myths and folk stories revisited the concept of wandering or shadowy worlds, tales of phantom planets or wandering spirits in the sky that might, metaphorically, echo the truth of planets unmoored from stars. Such stories reveal the enduring human fascination with the sky's mysteries, and the subtle recognition that not all cosmic dwellers fit neatly into established patterns. In many indigenous cultures around the globe, the sky has long been populated not only by stars and familiar planets, but also by cosmic entities that travel solitary paths, sometimes invisible, sometimes illuminating the night briefly with a glimpse of their passing. These narratives enrich our cultural tapestry and invite us to consider that the idea of rogue planets, silent wanderers in the cosmic dark, resonates deeply within human imagination. The interplay between ancient astronomical knowledge and mythology illustrates humanity's profound desire to explain the cosmos and its myriad lights and shadows. While no early civilization described rogue planets as we describe them now, the seeds of this wonder were planted in their observations of the unfamiliar stars, the errant wanderers, and the mysterious darkness lurking between the lights. With time and the development of scientific methods and technology, the wall of mystery began to lift, allowing scientists of the modern era to detect, study, and understand these dark nomads. Yet, as with many cosmic revelations, the mystery today builds on millennia of human curiosity and the patient observations of those who first looked upward and pondered the night. Moving forward, we will delve into how the modern foundation of planetary science grew from these ancient seeds, redefining what it means to be a planet, and how those concepts expanded to include even those worlds that wander alone in the darkness, setting the stage for our deepening understanding of the elusive rogue planets themselves. To truly appreciate the enigmatic nature of rogue planets, it is essential first to understand the foundational concepts of planetary science, what fundamentally defines a planet, and the processes by which these diverse worlds commonly come into existence. Planetary science is a multidisciplinary field that draws upon astronomy, geology, physics, and chemistry to explore how planets form, evolve, and interact within their cosmic neighborhoods. Grounding ourselves in these principles lays the pathway to understanding how some planets might end up as loners in the vastness of space. The simplest definition of a planet, as given by the International Astronomical Union, IAU, in 2006, holds three key criteria. To be classified as a planet, an object must orbit a star, possess enough mass for its own gravity to round it into a near-spherical shape, and have cleared the neighborhood around its orbit, essentially dominating its local region in space. This definition, while conceptually straightforward, underscores the deep connection between a planet and its host star. Yet, interestingly, this formal delineation excludes the class of rogue planets, cosmic wanderers that challenge the traditional criteria by virtue of their starless existence. But what are the physical and chemical ingredients that come together to form a planet in the first place? Planet formation begins within immense clouds of gas and dust scattered throughout our galaxy, known as molecular clouds. These chilly, dense regions, composed mainly of hydrogen and helium, act as stellar nurseries where stars ignite. Surrounding many newborn stars are circumstellar disks, rotating pancakes of leftover gas and dust spun out from the star's formation process. It is within these protoplanetary disks that planets take shape, a story written over millions of years. The two primary models of planet formation are the core accretion model and the disk instability model, each describing a fundamentally different pathway to planetary birth. Core accretion is the widely accepted process for forming planets similar to those in our solar system. Tiny dust grains within the circumstellar disk collide and stick together, gradually building up larger and larger solid bodies called planetesimals, objects roughly a kilometer or more across. Over time, these planetesimals collide and amalgamate into planetary embryos, kilometer-sized to moon-sized protoplanets. Gravity then subtly carves these embryos into the familiar full-sized planets by attracting further material, and, if the conditions are right, capturing thick gaseous envelopes to form gas giants. This gradual accretion is a complex, slow dance influenced by the disk's composition, temperature, and dynamics. In contrast, the disk instability model proposes a more rapid formation scenario, particularly for massive gas giants. In this concept, regions of the protoplanetary disk may become gravitationally unstable, collapsing almost directly into planet-sized clumps. This fragmentation can swiftly produce gaseous planets without the need to build a substantial solid core first. While this mechanism might not explain rocky terrestrial planets, it offers a compelling explanation for the rapid appearance of some massive gas giants in certain star systems. Once fully formed, planets often settle into near-stable orbits around their stars. Over billions of years, the architecture of a planetary system can be sculpted by gravitational interactions, migrations, and sometimes violent events that either clear the cosmic neighborhood or, intriguingly, lead to planets being ejected from their orbits altogether. Importantly, planets in our solar system display remarkable variety. Rocky terrestrial planets such as Mercury, Venus, Earth, and Mars are primarily composed of metals and silicates, bearing solid surfaces and dense interiors. Beyond the asteroid belt lie the gas giants Jupiter and Saturn, composed predominantly of hydrogen and helium, and the ice giants Uranus and Neptune, rich in volatile ices like water, ammonia, and methane. This compositional diversity is a direct outcome of the temperature gradients and material distribution in the protoplanetary disk. Moreover, the very process of planetary formation is influenced by the initial conditions of the star system: the mass and luminosity of the parent star, the chemical makeup of the natal cloud, and the dynamical environment in which the star and planets form. These factors determine how many planets form, their sizes, compositions, and orbital configurations. The standard planetary formation clearly requires a star as an anchoring center, a gravitational well that defines and shapes the birth and evolution of planets. From this standpoint, the existence of rogue planets, massive worlds adrift without a parent star, raises compelling questions about alternative formation pathways and catastrophic events that might unbind a planet from its star. Recent theoretical advances and observations suggest that while many planets follow this typical star-centered evolution, other processes, such as ejection by gravitational interactions or in situ formation within isolated gas clumps in interstellar space, may account for the presence of starless planets. Understanding the usual pathways of planet formation equips us with a baseline to appreciate these outlier phenomena. Another important aspect of planet classification hinges on mass thresholds. A planet must be massive enough for its self-gravity to overcome rigid body forces, forming a spherical shape, but not so massive that it triggers nuclear fusion, the hallmark of stars and brown dwarfs. This boundary lies around 13 times the mass of Jupiter, beyond which deuterium fusion can occur, making the object a brown dwarf rather than a planet. These nuances shape the definitions and investigations of starless planetary mass objects. Situating rogue planets in this framework illuminates their enigma. They may have formed like traditional planets, but lost their stellar companions, or alternatively emerged directly as isolated objects through mechanisms resembling star formation, but on a planet scale. The evolving understanding of planetary science continually expands its scope, revealing layers of diversity in planet formation and classification. In our continuing journey, we'll explore the exact nature of these starless wanderers, the distinctive characteristics that differentiate them from typical planets and other substellar objects. We'll delve into how these exceptions to planetary norms invite us to rethink the boundaries of planetary science and expand our imagination beyond the familiar. Thus, the foundations of planetary science, anchored in the concept of planets forming in the embrace of stars, serve as both the starting point and the contrasting backdrop to the fascinating, often paradoxical nature of rogue planets. They help us delineate the conventional from the extraordinary, offering a profound understanding of where these lone worlds fit within the grand celestial mosaic. Moving beyond the foundational principles of what defines a planet and how they typically form, we turn now to a remarkable category of planetary bodies that break the mold: rogue planets. These are worlds that wander the vast cosmic wilderness without the gravitational embrace of a host star. Freed from the conventional bonds that anchor planets within solar systems, rogue planets embody the fascinating essence of being bound to nothing. To understand what sets rogue planets apart, we must first grasp the question of what it means to be gravitationally bound. Most planets maintain their stable orbits by virtue of the gravity of a star, a powerful central force that dictates their paths and enables the rhythmic cycles of day and night, seasons, and climates. These stable, star-centered orbits allow planets to accumulate energy balances, hold atmospheres, and maintain conditions that, at least in some cases, favor the emergence of life. Rogue planets, in contrast, have no such central gravitational anchor. Instead, they drift freely through interstellar space, the immense stretches of near vacuum that separate star systems. They neither orbit a star nor constantly bask in its light and warmth. Instead, these dark nomads traverse the galaxy in solitude, journeying silently through the void. Defining a rogue planet involves recognizing several distinctive characteristics inherent to their nature. First and foremost is their lack of a host star. This decoupling from stellar gravity is a defining trait, effectively removing the planet from the radiative environment tied to stars. This means no sunlight reaches their surfaces, rendering them invisible in reflected light and extremely difficult to detect. The absence of stellar illumination also implies that the external energy source sustaining many familiar planetary processes is missing. Without a sun, rogue planets experience profound cold, with surface temperatures dropping to extremes rivaling or exceeding those found on distant dwarf planets and moons. Yet, intriguingly, some of these starless bodies may still harbor internal sources of heat that provide a subtle warmth beneath their frozen exteriors. Another important defining characteristic is their origin story, or rather the two leading possibilities for their origins. Some rogue planets may have formed within the protoplanetary disks of stars, but later suffered ejection through dynamical interactions such as gravitational perturbations or close encounters with other massive bodies. These planets were once part of star systems, but became unbound, cast adrift in the galaxy. Conversely, a subset may have formed in isolation from collapsing gas clouds, effectively born rogue, akin to a starless, planet-mass object forming independently in interstellar space. Due to their free-floating trajectory, rogue planets exhibit orbital dynamics vastly different from typical planets. Without the gravitational pull of a star, their paths through the galaxy are governed primarily by the collective gravitational influence of the Milky Way, passing stars, molecular clouds, and dark matter. Their trajectories are often eccentric and unpredictable, far removed from the orderly, elliptical orbits common within planetary systems. Physically, rogue planets span a range in size and composition. Their masses can vary widely, from objects smaller than Earth to those rivaling or exceeding Jupiter. Compositionally, they may mirror the types of planets found in star-bound systems, ranging from terrestrial, rocky worlds weighing heavily with silicates and metals, to gas giants cloaked in vast envelopes of hydrogen and helium. Some rogue planets might retain atmospheres heated by residual internal energy, while others could be completely frozen, turbulent deserts of ice and rock. Given their isolation, one might assume rogue planets to be dead and uninteresting. Yet, their defining characteristics suggest a more nuanced picture. Internally, some rogue planets may retain heat from gravitational contraction, radioactive decay, or residual formation energy. This internal heat could sustain geological activity, potentially keeping layers of subsurface ice molten, a subsystem reminiscent of the subsurface oceans detected beneath the icy crusts of moons such as Europa and Enceladus within our own solar system. This leads us to the tantalizing possibility that rogue planets could harbor niches of habitability, challenging the traditional view that life requires sunlight. Though their surfaces are scorched by cold, beneath thick ice shells they might host liquid water oceans, warmed by geothermal heat, universes unto themselves, isolated and dark, yet perhaps alive. Because rogue planets do not emit visible light or radiant energy in the same way stars do, detecting them requires indirect methods that exploit their subtle influences on surrounding objects or their emission of faint infrared radiation caused by internal warming. These observational challenges stem directly from their defining characteristic of being unbound. Furthermore, rogue planets sometimes blur the distinctions between other celestial objects, such as brown dwarfs, failed stars often classified between planets and stars by mass, and free-floating planetary mass objects. The defining characteristics of rogue planets thus include not only their unbound nature, but also their physical properties and formation histories that separate them from other classes of cosmic denizens. Unique among celestial bodies, rogue planets embody a state of cosmic independence, unmoored and drifting on paths determined by galactic forces rather than stellar confines. They represent one of the universe's most striking examples of solitude and endurance within the great cosmic wilderness. As we proceed, these defining characteristics will prove crucial in guiding our exploration of how astronomers detect such elusive objects, what clues reveal their solitary existence, and what implications they hold for planetary science, astrobiology, and our understanding of the dynamic galaxy we inhabit. The nature of being bound to nothing is at the heart of the Rogue Planet story, a story that will unfold layer by layer in the chapters ahead. The quest to detect rogue planets presents one of the most fascinating challenges in modern astronomy, an effort to identify the almost invisible. These cosmic nomads, wandering the galaxy unbound from any star, emit virtually no light of their own in the visible spectrum and do not reflect starlight, making them elusive to traditional detection methods that rely heavily on bright illumination. When confronted with objects as dark and solitary as rogue planets, astronomers must employ ingenious strategies to reveal their presence, often relying on subtle gravitational effects or faint emissions at infrared wavelengths. This pursuit has pushed technological innovation and theoretical understanding to the forefront, enabling discoveries that reshape our knowledge of the universe's architecture. Unlike planets tethered to stars, whose presence can be inferred from the wobbling motion of their parent stars or from the periodic dimming of starlight during transits, rogue planets float alone in the deep darkness of interstellar space. Without the radiance of a host star, there is no stellar light to dim or reflect. Without a bright beacon nearby, essentially no visible or optical signal returns to telescopes on Earth. This absence makes them some of the most challenging bodies to observe directly. One primary obstacle in detecting rogue planets is their inherent faintness. Objects in space are typically detected through the light they emit, reflect, or block. For bound planets, reflected starlight offers a detectable signature, while for stars and brown dwarfs, their own internal heat radiates primarily in the infrared. Rogue planets, especially smaller or cooler ones, may not emit sufficient infrared radiation to be visible with typical instruments. They recede into a cosmic backdrop filled with distant stars, galaxies, and interstellar dust, making them almost invisible. Moreover, the vast distances involved exacerbate these challenges. Even the nearest rogue planets would be tens to hundreds of light-years away, an unfathomable expanse, significantly dimming any radiation they produce. Furthermore, the relative velocities of rogue planets passing through the galaxy add complexity. Their paths are unpredictable, and they do not exhibit periodic signals as planets bound to stars do. Despite these hurdles, astronomers have pioneered several methods that exploit indirect evidence or creative observational techniques. One of the most effective avenues has been gravitational microlensing, a phenomena predicted by Einstein's theory of general relativity. When a massive object, like a rogue planet, passes precisely between a distant star and an observer on Earth, its gravity bends and magnifies the star's light in a manner akin to a cosmic lens. This microlensing event produces a temporary brightening of the background star, which can be detected by vigilant sky surveys. The duration and characteristics of the brightening provide clues about the intervening object's mass and motion, allowing astronomers to infer the presence of a planet-sized body, even if it emits no light itself. Microlensing has been instrumental in unveiling the first candidate rogue planets, as its sensitivity is well suited to detecting objects across vast distances and independent of emitted light. However, microlensing events are rare, transient, and difficult to predict, requiring long-term, wide-field monitoring of billions of stars to catch these brief brightenings. Confirming a rogue planet's existence through microlensing often demands careful analysis and multiple observations to rule out other explanations. Another approach employs deep infrared sky surveys using powerful space telescopes, such as the Wide-Field Infrared Survey Explorer, or WISE, and the Spitzer Space Telescope. These observatories scan large portions of the sky, detecting faint, cool objects radiating in the infrared. Some rogue planets, especially those massive and relatively young, retain enough internal heat to emit detectable infrared radiation. By filtering out background noise and identifying faint-moving objects, astronomers can spot potential rogue planets, though distinguishing them from distant brown dwarfs or stellar remnants requires further spectral analysis. Direct imaging, a method successful in capturing exoplanets orbiting young, bright stars, finds limited applicability with rogue planets due to the absence of a luminous host star for contrast. Nevertheless, projects focusing on the coldest and nearest objects continue to push observational thresholds, occasionally capturing images of free-floating planetary mass objects that may be rogue planets or low-mass brown dwarfs. The use of astrometry, the precise measurement of an object's position in the sky over time, also offers promise. As rogue planets pass near stars, their gravitational influence could induce subtle shifts in the star's position, detectable with advanced instruments like the Gaia Space Observatory. Though challenging due to the weak gravitational pull of planets compared to stars, such detections could eventually identify rogue planets as they transit near the line of sight. Beyond the challenges of detection lie breakthroughs resulting from technological advancement and international collaboration. Dedicated microlensing surveys, including the optical gravitational lensing experiment, OGLE, and the microlensing observations in astrophysics, MOA, have systematically searched dense star fields in the Milky Way's bulge to catch microlensing events. Their efforts have singled out intriguing candidates consistent with rogue planets, suggesting these objects may be more common than previously thought. Furthermore, planned and upcoming missions promise to revolutionize our abilities. The Nancy Grace Roman Space Telescope, for example, is designed to conduct precise microlensing surveys with unprecedented sensitivity and breadth. Its observations are expected to uncover numerous rogue planets, ranging from Earth-sized to several times Jupiter's mass, enabling a statistical census that will richly inform theories of planet formation and galactic dynamics. In addition, advances in infrared detector technology and data processing techniques, including machine learning, augment the potential for identifying subtle signals of rogue planets amidst the cosmic noise. Large-area sky surveys, both from space and ground-based observatories, are steadily building a more comprehensive picture of the galactic population of free-floating planetary bodies. Despite the formidable obstacles, the pursuit of rogue planets has progressively shifted from speculative theory to empirical inquiry. With each new candidate discovered and methodology refined, the veil of darkness gradually lifts from these lonely cosmic wayfarers, yet much remains to unveil. Their distribution, masses, compositions, and origins continue to challenge astronomers. Our understanding of rogue planets and their elusive nature highlights the ingenuity and persistence at the heart of astronomical exploration. It embodies humanity's enduring commitment to illuminating even the faintest and most hidden corners of the universe. As technology advances and our observational reach extends, the future stands bright with the promise of uncovering many more of these shadowy wanderers, expanding our cosmic perspective and deepening our appreciation of the dynamic and mysterious galaxy we call home. Having explored the formidable challenges and innovative breakthroughs in detecting dark, solitary planets, we now turn our attention to the specific marvel of gravitational microlensing. the technique that first unveiled the presence of these starless wanderers and unlocked new avenues for their discovery. In the vast theater of the cosmos, rogue planets drift silently through the darkness, invisible to traditional telescopes and eluding standard observational methods that rely on starlight reflected or emitted. The discovery of these elusive objects demanded a breakthrough, an observational technique so sensitive that it could detect the presence of objects not by their own light, but by their gravitational influence. This breakthrough came in the form of gravitational microlensing, a phenomenon whose subtle magic unveiled the first compelling candidates for rogue planets and opened a new window into the unseen population of lone worlds roaming the galaxy. The story of microlensing begins with a fundamental prediction of Einstein's general theory of relativity. Massive objects bend the fabric of space-time around them, causing light from a more distant source passing nearby to be bent, much like the way a lens focuses or distorts rays of light. Unlike the more familiar strong gravitational lensing seen around massive galaxy clusters that produce multiple images or arcs, microlensing occurs when a much smaller massive body, like a star, brown dwarf, or planet, passes closely along the line of sight to a background star. This effect causes a temporary and subtle brightening of the background star's light without splitting it into multiple images. This brightening event, known as a microlensing event, can last from days to weeks depending on the mass and relative velocity of the intervening object. The light curve, the graph of brightness over time, has a distinctive symmetrical shape, peaking when the lensing object is closest to the background star's position. By carefully analyzing the shape, duration, and intensity of the event, astronomers can infer characteristics of the lensing body, such as its mass and distance, even when it emits no detectable light. Microlensing became a powerful tool for detecting dim, isolated, and otherwise invisible objects in the late 20th century, as large monitoring surveys were established to hunt for dark matter candidates and exoplanets. One of the pioneering projects was the optical gravitational lensing experiment, OGLE, initiated in the early 1990s, which monitored millions of stars in the dense stellar fields of the Milky Way's bulge. Another key project, the microlensing observations in astrophysics, MOA, complemented this effort with dedicated telescopes and rapid data processing techniques. While initial microlensing detections primarily focused on stars and binaries, the technique's sensitivity to lower mass objects soon brought planets into view. The telltale sign of a planet in a microlensing event is a brief secondary deviation in the light curve, often lasting just hours or days, indicating the presence of a smaller companion to the primary lensing star. However, when an object is truly free-floating with no host star, the microlensing event takes on a different character. It is shorter in duration and manifests solely from the planet's gravitational field. In 2011, a remarkable breakthrough occurred when a team led by astronomers utilizing data from the MOA and OGLE surveys announced statistical evidence for a population of free-floating planets. By analyzing thousands of microlensing events, they identified a subset with unusually brief durations, consistent with objects approximately the mass of Jupiter, but with no detectable host stars influencing the light curves. This suggested the presence of a vast number of rogue planets in the Milky Way, potentially outnumbering stars. This discovery was groundbreaking not only because it confirmed the existence of rogue planets, but also because it revolutionized the method of studying them. Microlensing offered a way to detect starless worlds far beyond the reach of direct imaging or traditional exoplanet methods. Moreover, it imparted mass information unattainable through other means, allowing astronomers to estimate the sizes and quantities of these elusive wanderers. Yet, microlensing has its challenges. Microlensing events are serendipitous and unpredictable. It relies on chance alignments with distant stars, and the alignment must be perfect within a fraction of an arcsecond. The events are transient, lasting from hours to weeks, making continuous wide-field survey monitoring essential. Additionally, distinguishing between rogue planets and bound planets or other small objects requires precise modeling and often complementary observations. Despite these challenges, advancements in wide-field surveys, real-time data analytics, and international collaborations have steadily improved the efficiency and accuracy of microlensing observations. Upcoming space missions like the Nancy Grace Roman Space Telescope are designed with microlensing surveys as key components, promising thousands of new detections with unprecedented sensitivity. This next generation of microlensing studies is expected to not only confirm more rogue planets, but also shed light on their mass distribution, origins, and space density. Microlensing also deepens our understanding of planetary system evolution. By identifying planets that have escaped their stars, it reveals the chaotic dynamical processes in young planetary systems that can eject planets into interstellar space. Moreover, microlensing surveys contribute to mapping the demographics of planetary bodies throughout the galaxy, offering clues to the frequency and variety of planetary formation mechanisms. In essence, the microlensing magic transforms the invisible into the observable. It harnesses the invisible threads of gravity stretching across light years to reveal solitary planets otherwise cloaked in darkness. The technique stands as a luminous beacon in the quest to chart the loneliest worlds and has inaugurated a new chapter in planetary science where the cosmic nomads are no longer myths, but measurable entities. As we reflect on this revolutionary technique, it becomes clear that microlensing has opened a portal into the unseen realms of our galaxy, giving humanity eyes to detect the invisible and ears to listen to the silent stories of rogue planets. From here, we are poised to explore how these discoveries have unfolded over time, tracing a timeline of the major rogue planet detections and the growing understanding of their enigmatic existence. Tracing the discovery of rogue planets reveals a fascinating timeline, marking milestones that transformed what was once speculative into a field rich with concrete evidence and growing understanding. Surveys dedicated to monitoring the cosmos, combined with groundbreaking theoretical insights and technological advancements, have gradually unveiled the existence and properties of these free-floating starless worlds. This chapter in astronomical history not only chronicles key discoveries, but also illuminates the evolution of scientific methods and perspectives regarding the galaxy's loneliest inhabitants. The story begins in the late 20th century, amid the rise of massive sky surveys and the development of gravitational microlensing as a robust observational technique. Although the concept of starless planets drifting through interstellar space can be traced back decades in theoretical studies, empirical confirmation would require patient, painstaking observations over many years. In the early 1990s, large-scale monitoring projects such as the Optical Gravitational Lensing Experiment, OGL, in Poland, and the microlensing observations in astrophysics, MOA, in Japan, began systematic surveys of dense stellar fields, particularly in the Milky Way's central bulge. Their objective was to detect microlensing events, those brief brightenings of distant stars caused by foreground gravitational lenses. Initially, the focus centered on detecting dark matter candidates and stellar populations, but soon the sensitivity of these surveys made them capable of identifying planetary mass objects as lenses as well. Throughout the late 1990s and early 2000s, these surveys recorded thousands of microlensing events, with particular intrigue arising from unusually brief events whose durations suggested low-mass lenses consistent with free-floating planets. Yet, individual event data alone often proved inconclusive, making the existence of rogue planets a subject of debate. A major breakthrough came in 2011 when a combined analysis of OGLE and MOA data revealed a statistically significant overdensity of short-duration microlensing events. This landmark study, led by astronomers including Kei Sumi and colleagues, posited the presence of a vast population of Jupiter-mass rogue planets roaming the Milky Way, potentially outnumbering stars themselves. This was the first compelling statistical evidence elevating rogue planets from theoretical possibility to astronomical fact. Following this revelation, attention turned to confirming individual rogue planet candidates and understanding their distributions and characteristics. In 2012, observations by NASA's Wide Field Infrared Survey Explorer, WISE, and ground-based telescopes identified some isolated planetary mass objects in young star-forming regions. These objects, sometimes called free-floating planetary mass objects, or sub-brown dwarfs, blurred the lines between rogue planets and brown dwarfs, but hinted at diverse formation pathways. One notable example is PSO J318.522, discovered in 2013, a young, free-floating object approximately 6 times the mass of Jupiter, residing about 80 light-years away. Although it does not orbit a star, its spectral properties resemble those of giant exoplanets, reinforcing the idea of rogue bodies that formed or were ejected early in their system's history. Meanwhile, deep imaging surveys, such as those conducted with the Very Large Telescope and the Hubble Space Telescope in star clusters, have uncovered additional isolated planetary mass objects, providing crucial data on their prevalence and characteristics. These observations support theories that some rogue planets may form in situ, directly from gravitational collapse, rather than being solely the products of ejection from star-bound orbits. More recently, advances in infrared astronomy and space telescope missions have enhanced our ability to detect cooler, fainter rogue planets. The European Space Agency's Gaia telescope, launched in 2013, has contributed by precisely mapping stellar motions, enabling the identification of gravitationally perturbed stars that may harbor or have interacted with rogue planets. As of the early 2020s, the population estimates for rogue planets vary, but suggest they could be as numerous as the stars in our galaxy, numbering in the billions. This realization has profound implications for planetary formation theories, galactic dynamics, and astrobiology. Looking forward, upcoming missions promise to accelerate discovery dramatically. The Nancy Grace Roman Space Telescope, planned for the mid-2020s, will conduct wide-field microlensing surveys capable of detecting thousands of rogue planets, including those Earth-sized and smaller, previously beyond reach. Coupled with next-generation observatories such as the James Webb Space Telescope and the Vera C. Rubin Observatory, our capacity to discover, characterize, and understand rogue planets is poised for an unprecedented leap. Thus, the timeline of rogue planet discoveries is a narrative woven from decades of methodical sky monitoring, technological innovation, and theoretical insight. From statistical hints in microlensing data to direct observations of isolated planetary mass objects, the past 30 years have transformed the concept of these cosmic nomads from curious speculation into a vibrant domain of study, opening new frontiers in our understanding of planetary systems and the galaxy's hidden population of lonely worlds. As we move beyond this timeline, the story deepens into quantifying their numbers, probing their formation, and unraveling the intricate dynamical processes that cast these planets adrift, a journey that continues to reveal the vast and varied nature of our cosmic neighborhood. Estimating the population of rogue planets within our Milky Way is akin to counting the shadows cast in moonless night, an exercise in discerning the invisible amid profound cosmic darkness. These solitary wanderers elude direct observation, and yet their numbers carry significant implications for our understanding of planetary formation, galactic dynamics, and even the potential for life beyond the light of stars. Through a synthesis of observational data, theoretical models, and statistical inference, astronomers have strived to illuminate the vast, unseen population of rogue planets scattered throughout our galaxy. To begin with, the challenges inherent in detecting rogue planets shape our methods of estimation. Because these planets emit little or no visible light and do not orbit stars, conventional detection techniques, such as transit photometry, radial velocity measurements, or direct imaging, prove ineffective or limited. Instead, astronomers rely on indirect methods, most notably gravitational microlensing, to infer their prevalence. Microlensing surveys have unveiled compelling statistical evidence that rogue planets may be surprisingly numerous, potentially rivaling or even exceeding the number of stars in the galaxy. One of the pioneering studies leveraging microlensing data was conducted by the MOA and OGLE collaborations. Analyzing thousands of microlensing events observed toward the dense stellar field at the center of the Milky Way, researchers identified a significant population of extremely short-duration events consistent with planetary mass objects unbound to any star. This led to the startling estimate that there could be nearly 2 rogue Jupiter-mass planets for every star in the Milky Way. Such a prolific population challenges traditional views and suggests galaxy-wide processes actively produce or release these bodies. However, these early estimates carry significant uncertainties. Microlensing is sensitive largely to free-floating planets within a limited mass range. Typically, Earth to Jupiter masses and observational biases affect event detection rates. Moreover, differentiating between true rogue planets and distant bound planets in wide orbits remains challenging. Despite these complexities, the measurements firmly established that free-floating planets are an abundant galactic component. Complementing microlensing, surveys of star-forming regions and young stellar clusters have identified free-floating planetary mass objects with masses as low as a few times that of Jupiter. For instance, in nearby clusters such as the Sigma Orionis and Taurus Auriga, dozens of planetary mass bodies independent of stars have been catalogued through deep infrared and optical imaging. These findings imply that some rogue planets form in isolation, born as starless bodies directly from collapsing molecular clouds, rather than solely as escapees from planetary systems. Further constraints on the rogue planet population arise from models of planet formation and system dynamics. Computer simulations of the chaotic young phases of planetary systems indicate that gravitational interactions frequently eject planets, especially during periods of instability caused by giant planet migration or close stellar encounters. These dynamic ejections could populate the galaxy with a considerable number of rogue planets over billions of years. Nevertheless, quantifying the total number hinges on assumptions about star formation efficiency, initial planetary system architectures, and the frequency of violent gravitational disturbances. Models attempting to incorporate these factors suggest a wide range, from a few billion up to hundreds of billions of rogue planets across the Milky Way's 100 billion stars. This uncertainty underscores the diversity of possible galactic histories and the speculative nature of extrapolating limited observations. Infrared all-sky surveys conducted by missions like NASA's Wide Field Infrared Survey Explorer, WISE, have placed limits on the population of relatively nearby and warm rogue planets. Their sensitivity reveals that while massive, young rogue planets should be detectable within a few dozen light-years if they existed, such nearby bodies are rare or absent, implying that either the population is dominated by lower mass or much older and colder objects, or that such objects are distributed more sparsely in our neighborhood. The mass distribution of rogue planets also influences population estimates. If the rogue planet population primarily consists of gas giants akin to Jupiter, their individual detection probabilities differ substantially compared to a population skewed toward Earth-sized or smaller bodies. The existence of lower-mass rogue planets is inferred, but remains difficult to detect with current methods, leaving a large portion of the population effectively hidden. Recently, advances in astrometric missions like ESA's Gaia telescope have begun to refine our understanding of local stellar kinematics and possible perturbers. While direct detections of rogue planets by astrometry remain challenging, their gravitational influence on stars may help constrain their numbers indirectly in the coming years. Summing these inputs, astronomers conclude that the Milky Way likely hosts billions of rogue planets, perhaps rivaling or exceeding the number of stars. Estimates remain broad, ranging from a few to tens of rogue planets per star. But the consensus grows that these free-floating worlds form a substantial, albeit hidden, galactic population. The implications are profound. Such a vast number of isolated worlds suggests that planetary system formation is not a closed process, but one marked by dynamic exchanges and expulsions. It also extends the boundaries of planetary habitability theories, as some of these planets might carry internal heat sources, enabling distant, cold niches for life. Moreover, this vast, unluminous population influences galactic mass distribution and dynamics more than previously recognized. As astronomical technology advances, especially with the launch of next-generation observatories dedicated to microlensing and infrared surveys, the veil shrouding the population of rogue planets is expected to lift. Precise census-taking missions will refine these numbers, reveal the mass spectrum in finer detail, and illuminate the formation and evolutionary histories of these dark travelers. In contemplating the sheer scale of the rogue planet population, we are reminded of the universe's proclivity for surprises. These lonely planets, adrift and unseen, challenge our notions of what it means to be a world, where it can exist, and how common such isolation might be. As our tools sharpen and surveys deepen, we will step ever closer to fully mapping these numbers in the dark, bringing light to the galaxy's silent wanderers and enriching our understanding of the grand cosmic balance. Having considered the scope and scale of the rogue planet population, the next step in our cosmic voyage is to explore the intriguing ways in which these worlds come to be set adrift. The formation theories that explain how planets become unmoored from their stellar cradles and begin their solitary journeys across the galaxy. As we contemplate the vast population of rogue planets drifting through the Milky Way, a natural and profound question emerges. How do such worlds come to be set adrift in the cosmic wilderness, severed from the gravitational embrace of a star? Understanding the formation mechanisms behind rogue planets unlocks insights into planetary system dynamics, the processes shaping our galaxy, and even the broader cosmic cycles of creation and destruction. While the existence of planets unmoored from stars might initially seem contrary to conventional planetary science, several well-founded theories explain their origin, weaving a narrative of dynamic interactions, violent ejections, and even solitary births in the cold depths of interstellar space. Broadly speaking, there are two prevailing formation pathways for rogue planets: ejection from bound planetary systems and direct formation in isolation. Each mechanism reflects distinct processes and conditions, but can both contribute to the rogue planet population. The first and most widely accepted pathway involves planets forming within protoplanetary disks around stars, much like the planets in our own solar system, but subsequently being gravitationally scattered and ejected into interstellar space. During the early chaotic stages of planetary system evolution, young planets often interact with each other and with other massive bodies, such as neighboring stars, especially within dense stellar nurseries where stars form in clusters. These gravitational interactions can abruptly disrupt the orbits of some planets, particularly those in unstable orbits or with large masses, hurling them onto escape trajectories from their parent systems. Computer simulations of such dynamical evolution reveal that multi-planet systems frequently experience periods of instability, where close encounters and resonances among planets lead to collisions, orbital swaps, or ejections. Giant planets like Jupiter play outsized roles in this process. Their substantial gravity can destabilize other bodies or themselves be scattered. Similarly, encounters between stars in crowded clusters can gravitationally perturb planetary systems, increasing the likelihood of planets being ejected. While some ejections occur early, during the formative hundreds of millions of years, others might happen over much longer timescales as systems evolve. These violent processes, sometimes described as cosmic pinball games or gravitational slapshots, efficiently produce populations of rogue planets. The frequency of ejection depends on numerous factors, including planetary system architecture, the number and mass of planets, the birth environment's density, and the presence of stellar companions. Adding complexity, some ejected planets might carry with them circumplanetary material, potentially even forming moons or retaining atmospheres if conditions allow. These primordial traits could influence the rogue planet's subsequent evolution and potential habitability. The second primary origin hypothesis posits that rogue planets can form directly in isolation, much like stars or brown dwarfs, from the gravitational collapse of molecular cloud fragments too small to ignite nuclear fusion. In regions dense with gas and dust, turbulent conditions can produce clumps with masses ranging from several Jupiter masses to many times that, enough to coalesce into objects with planetary masses. These so-called starless planetary mass objects challenge traditional distinctions between planets and sub-brown dwarfs, highlighting a continuum of object formation across mass scales. Observations of young star-forming regions provide evidence supporting this scenario, where free-floating planetary mass objects appear alongside stars and brown dwarfs. Such bodies may represent the low-mass tail of star formation rather than failed planets ejected from systems. They often show properties similar to gas giant planets, but lack a central host star. This direct formation route suggests that some rogue planets have never been gravitationally bound to stars and have instead been solitary wanderers since their birth, a striking reversal of the typical planetary origin story. The frequency with which such objects form depends on cloud fragmentation physics, turbulence scales, and the complex interplay of gravity, radiation, and magnetic fields in molecular clouds. Beyond these primary theories, other processes contribute to the creation of rogue planets. For instance, collisions between planets or protoplanets within young systems can eject debris or whole planetary bodies into space. The death throes of stars, such as supernova explosions or the expansion phases of giant stars, might destabilize orbits of surviving planets, flinging them into interstellar space. Even tidal interactions between stars passing close to planetary systems can disrupt or capture planets, reshaping the galactic landscape of free-floating worlds. Modern computer simulations have become invaluable in exploring these complex mechanisms, modeling the dynamical ballet within star clusters and the intricacies of cloud fragmentation. They reveal that the ejection of planets is commonplace, and that the population of rogue planets in the galaxy likely results from a mixture of formation channels. Understanding these formation pathways also has profound implications for astrobiology. Ejected planets might carry biosignatures, or subsurface oceans preserved from their former stellar systems, while star-formed rogue planets may represent primordial environments that are chemically simpler or vastly different. In conclusion, the setting adrift of worlds, through violent scattering, solitary birth, or the ravages of stellar evolution, is a testament to the dynamic and often tumultuous nature of our galaxy. Rogue planets are more than cosmic curiosities. They are key witnesses to the forces shaping planetary systems and stellar neighborhoods. Grasping how they come to roam the interstellar void expands our appreciation of planetary diversity and the resilience and creativity of nature across cosmic timescales. With these captivating formation theories in hand, we are ready to examine how astronomers differentiate rogue planets from other celestial objects sharing similar properties, such as brown dwarfs or failed stars, a subtle but crucial task in the ongoing exploration of the cosmos. In the grand cosmic classification of celestial bodies, the boundaries between planets, brown dwarfs, and failed stars can often become blurred, especially when considering objects that wander through the galaxy without the warmth of a host star. Among these enigmatic wanderers, rogue planets occupy a fascinating niche, yet distinguishing them from their close cousins, brown dwarfs and failed stars, requires careful delineation of characteristics, origins, and physical properties. Understanding these distinctions elucidates not only classification schemes, but also the diverse evolutionary paths through which these objects emerge in our galaxy. At first glance, rogue planets, brown dwarfs, and very low-mass stars share a number of morphological and physical traits. All can possess masses larger than Earth, be roughly spherical due to their own gravity, and exist independently in space, free from stellar companionship. Yet their origins, mass ranges, internal processes, and observational signatures reveal crucial differences. Defining a planet based on current consensus primarily involves factors such as mass, formation history, and whether the object directly orbits a star. Rogue planets, by definition, are planet mass objects unattached to any star, either ejected from a planetary system or formed independently outside of stellar influence. A key mass threshold is set by the deuterium burning limit, approximately 13 times the mass of Jupiter. Above this mass, an object is capable of fusing deuterium, an isotope of hydrogen to some extent, placing it in the brown dwarf regime rather than planet territory. This nuclear capability distinguishes brown dwarfs from planets, as brown dwarfs represent failed stars that did not gain enough mass to sustain hydrogen fusion but could briefly burn deuterium. Brown dwarfs therefore bridge the gap between the heaviest planets and the lightest stars, with typical masses ranging from about 13 to 75 Jupiter masses. Unlike planets, brown dwarfs generally form through the gravitational collapse of molecular clouds, similar to stars, not via accretion processes in circumstellar disks. This difference in formation pathway is paramount in classification debates, although it remains challenging to observe directly, as the formation history cannot be easily discerned by present observations. Failed stars, often a term used to describe brown dwarfs, occupy this intermediate mass and behavior regime. Unlike bona fide stars, they do not sustain sustained thermonuclear fusion of hydrogen in their cores, but share many characteristics of young, low-mass stars, such as their atmospheric properties and cooling evolution. Over time, brown dwarfs radiate away residual heat and shrink, bright in infrared but invisible in optical light after cooling for billions of years. On the other hand, rogue planets, especially those below the 13 Jupiter mass threshold, lack the capacity for any kind of fusion. Their internal energy results primarily from residual heat of formation, radioactive decay, and gravitational contraction, gradually cooling and darkening over time. Rogue planet sizes often remain close to that of Jupiter, regardless of mass variations, because gravity compresses their interiors. Thus, radius alone is insufficient for categorization. Distinguishing these objects observationally requires a combination of measurements: mass estimates, atmospheric characterization via spectroscopy, luminosity, temperature, and sometimes orbital context when available. For instance, brown dwarfs typically exhibit spectral signatures of methane, water vapor, and ammonia in their atmospheres, features that overlap with gas giant planets but differ in relative intensity and temperature profiles. The detection of certain spectral lines and measurement of gravity-sensitive features allows astronomers to infer surface gravity and composition, helping to differentiate brown dwarfs from massive planets. Additionally, brown dwarfs tend to be younger and hotter than rogue planets, radiating primarily in the infrared, which can be detected by telescopes tuned for such wavelengths. However, ambiguity often arises. Objects at the borderline masses and temperatures can masquerade as either category, especially when isolated or with limited observational data. In some cases, observational campaigns reveal objects in star-forming regions that challenge classification, possibly representing planetary mass brown dwarfs or planetary mass rogue worlds born through direct cloud collapse. Formation history remains a fundamental but elusive discriminator. Planets generally form via accretion within protoplanetary disks around stars, building mass gradually from dust to planetesimals to planets, whereas brown dwarfs form like stars, condensing rapidly from molecular clouds. Yet, without an orbiting star or evidence of formation environment, distinguishing between a rogue planet ejected from a planetary system and a free-floating planetary mass brown dwarf can be impractical. Researchers have proposed astrophysical tests to clarify classifications, such as examining an object's kinematics and location relative to star-forming clusters. An object found in isolation amidst a star-forming region with characteristics suggesting young age may be a planetary mass brown dwarf. Conversely, older objects scattered broadly within the galactic field may more likely be ejected rogue planets. Nonetheless, overlaps persist. In recent years, advanced infrared observatories and spectrometers, like the James Webb Space Telescope, offer enhanced tools to resolve these puzzles by probing atmospheric compositions, temperature profiles, and thermal histories with unprecedented precision. Cloud patterns, weather phenomena, and chemical fingerprints all become vital clues in the quest to classify starless planetary mass objects accurately. In sum, the distinctions between rogue planets, brown dwarfs, and failed stars represent a nuanced interplay between mass, formation, and physical properties, complicated by observational constraints. Understanding these planetary isomers broadens our insight into the galaxy's small bodies and challenges the neat categorical boxes once thought definitive. It also invites us to appreciate the continuum of cosmic objects and the complex processes that govern their births and lives. As this chapter closes, we prepare to delve into one of the major cosmic sculptors behind rogue planet creation, the tidal drama enacted by gravitational interactions and stellar evolution, dynamic forces capable of unbinding planets and sending them into their lonely interstellar journeys. In the cosmic dance of the galaxy, planets, stars, and other celestial objects are bound in a continual interplay of gravitational forces, each movement sending ripples through their surrounding environment. Among these forces, gravitational interactions and the evolving life cycles of stars play a pivotal role in sculpting planetary systems, and sometimes in casting certain worlds adrift to roam the galaxy as rogue planets. This tidal drama is a fundamental aspect of how some planets become untethered, illustrating the dynamism and occasional violence woven into cosmic evolution. Gravity, the invisible but unyielding architect of planetary orbits, mediates the relationship between planets and their stars. Stable planetary systems exist when these gravitational forces balance, holding planets in regular, often near-circular orbits. Yet, gravitational interactions can quickly spiral into complexity when multiple massive bodies influence one another, particularly in densely populated star clusters or systems with multiple large planets. In such environments, perturbations can destabilize planetary orbits, leading to orbital eccentricities, collisions, or catastrophic ejections. One of the most significant agents of this tidal drama is the process known as gravitational scattering. When two or more planets in the same system approach closely, their mutual gravitational forces cause sudden accelerations and deflections. If one planet gains enough kinetic energy during these encounters, it may be propelled beyond the sobering reach of its parent star's gravity, entering the interstellar void as a rogue planet. This phenomenon is especially prevalent in young planetary systems, where newly formed planets are still settling into stable configurations amid the chaos of remaining debris and gravitational tugs. Beyond interactions within planetary systems, external gravitational influences also play a critical role. During the formative years of stars, many are born within dense clusters, teeming with sibling stars in close proximity. Encounters between stars, a cosmic near miss, in such crucibles can exert tremendous tidal forces on surrounding planetary systems. These stellar flybys can strip planets from their orbits or send them spiraling into unstable trajectories. Close stellar encounters are like gravitational gambits, shaking planetary systems to their cores and often ejecting planets into interstellar space. Throughout stellar evolution, stars themselves change dramatically, exerting varying gravitational effects on their planetary families. As stars exhaust their nuclear fuel, they undergo phases such as the red giant expansion, during which a star swells enormously in size. This expansion can engulf inner planets, vaporizing them or gravitationally disrupting their orbits. The loss of mass from stellar winds during such stages weakens the star's gravitational grip, allowing remaining planets to drift outward or become unbound. Consequently, stellar evolution is a key mechanism potentially converting bound planets into rogue vagabonds. Moreover, the violent demise of stars via supernova explosions can radically reshape their planetary systems. The sudden ejection of massive stellar material and the abrupt loss of mass drastically alter the gravitational field, flinging planets onto escape trajectories. Such catastrophic events hurl planets into interstellar space with tremendous velocities, contributing to the population of roving planets. The role of tidal interactions extends further to binary and multiple star systems, where complex gravitational dynamics prevail. In these systems, planets may experience fluctuating gravitational pulls from multiple stars, destabilizing their orbits. These perturbations, over millions of years, can lead to planet ejections or orbital reshaping akin to a cosmic pinball machine. State-of-the-art computer simulations have been indispensable in unwrapping these tidal dramas. By modeling thousands of years of planetary interactions within evolving stellar environments, scientists reproduce scenarios where ejections occur frequently. These models demonstrate how subtle changes, small variations in planetary masses, orbital distances, or cluster encounter rates, can tip the delicate balance, illustrating the fragile dynamical states of planetary systems. Empirically, observations of exoplanet systems with eccentric or highly inclined orbits or gaps point to histories of gravitational perturbations and past ejections. Some rogue planets might thus be survivors of such celestial chaos, their journeys beginning as planets fettered to stars, later liberated by the intertwined forces of gravity and stellar evolution. Understanding this tidal drama deepens our appreciation of rogue planets not as isolated oddities, but as integral actors in the evolving narrative of galaxies. They testify to the imperfections and upheavals inherent to planetary birth and survival, embodying the restless nature of the cosmos. As we continue, this story of gravitational dynamics leads naturally into the exploration of even more violent origins, the cosmic collisions and close encounters that propel planets into their rogue existence, illuminating the extreme interplays that shape the population of loneliest worlds. In the endless theater of the cosmos, where stars are born and planets coalesce, the scene is not always serene. Instead, it often unfolds as a spectacularly violent saga, characterized by collisions, close encounters, and chaotic gravitational interactions, which collectively delineate what astronomers evocatively term the cosmic pinball effect. This relentless bombardment and scattering of celestial bodies play a crucial role in shaping planetary systems and is a principal architect behind the creation of rogue planets. To understand these violent origins is to peer into the turbulent heart of planetary dynamics and appreciate the tumultuous forces that can hurl worlds into solitary journeys across interstellar space. During the early epochs of a star system, as dust and gas in the protoplanetary disk coalesce into planetesimals and embryos, the environment is crowded and unstable. Gravitational interactions between these growing bodies are frequent and intense. Unlike the calm and steady orbits planets settle into billions of years later, the youth of planetary systems is marked by orbital crossings, close encounters, and sometimes catastrophic collisions. These interactions can drastically alter trajectories, both within the system and beyond, leading to feedback loops of instability. Collisions between planetary embryos are common in this chaotic environment and are foundational to the eventual formation of terrestrial planets. Yet, not all collisions result in accretion or growth. Violent impacts can shatter bodies, scatter debris, and create new possibilities for orbits that barely hold on to their stars or lose them entirely. A sufficiently energetic gravitational nudge, perhaps following a collision or near miss, can send a planet or planet-sized object careening out of its stellar system entirely. The cosmic pinball effect metaphor encapsulates the often unpredictable and stochastic nature of these interactions. Just as a pinball machine sends its ball bouncing unpredictably among bumpers and flippers, planetary bodies are struck by gravitational forces from their neighbor planets, passing stars, and the galactic tidal field. These forces can amplify or dampen orbital eccentricities and inclinations, leading to scenarios where planets are sent plunging inward toward their host star, collide with siblings, or are ejected altogether. Close encounters, especially among giant planets, can be particularly disruptive. When two or more massive planets pass near each other, their mutual gravity can drastically modify their orbits. In these gravitational flybys, energy is exchanged rapidly, and one planetary body may gain enough velocity to escape its star's gravitational grip. This process not only accounts for some planets becoming rogue, but also explains highly eccentric orbits observed in known exoplanet systems. Further compounding dynamics, the birth clusters of stars, dense conglomerates where stars form in proximity, provide fertile grounds for close stellar encounters. As stars pass each other at relatively close distances, their gravitational fields interact, perturbing the orbits of planets and smaller bodies around them. Such encounters can destabilize planetary orbits, trigger ejections, or even capture planets from neighboring systems, contributing to the population of rogue planets or unusual planetary arrangements. The violent origins of rogue planets are also linked to the violent endings of stars. Supernovae, Cataclysmic explosions marking the deaths of massive stars emit intense blast waves and shed large fractions of stellar mass in short times. Planets orbiting such stars may suddenly find their gravitational anchor insufficient to retain them, sending them adrift. Similarly, asymmetric mass loss in less massive stars evolving into white dwarfs can reduce gravitational binding and destabilize planetary orbits, potentially resulting in ejections. Astronomical simulations have played a pivotal role in unraveling these violent origins. By modeling multi-body systems with realistic initial conditions and tracking their evolution over millions to billions of years, simulations reveal that planetary ejections are not rare exceptions, but rather natural outcomes of planetary system development. They demonstrate that systems with multiple giant planets are particularly predisposed to scattering events, leading to rogue planet formation. Such studies refine our understanding of planetary system architectures and highlight the fragility and dynamism inherent to planetary orbits. They also offer explanations for observed exoplanets with misaligned, highly elliptical, or unusual orbits, signatures of past violent disruptions. From an observational standpoint, these violent origins underscore why rogue planets are likely common in galaxies like ours, born not solely from direct starless collapse, but also as casualties of turbulent planetary evolution and stellar life cycles. Each rogue planet is, in essence, a survivor of dramatic episodes echoing the violent history of its origin system. As we move forward, exploring how rogue planets transition from their stellar cradles to making their solitary passages through the galaxy, we delve into the rich simulation studies modeling their journeys and uncover the complexity of their solitary existence in the cosmic wilderness. To truly grasp the journey of rogue planets, from their birth within the dense, swirling clouds of stellar nurseries to their solitary wanderings through the vast galactic expanse, scientists turn to the powerful tools of numerical simulations. These computer models allow us to recreate, in exquisite detail, the complex physical processes and dynamical interactions that eject planets from their birthplaces and set them adrift in interstellar space. Through these simulations, we unveil the rich cosmic story of rogue planets, tracing their origins, evolution, and ultimate fate as galactic travelers. Stellar nurseries are bustling, chaotic regions where vast molecular clouds collapse under gravity, birthing stars and their accompanying planetary systems. Population densities here are high, and young stars often form in clusters, separated by relatively small distances on astronomical scales. This crowded environment is ripe for dynamical interactions, making it an ideal setting to investigate how planets might be cast away from their host stars. Simulations begin by modeling the collapse of molecular clouds, the formation of stars, and the accretion disks that give rise to planets. High-resolution hydrodynamic codes track gas dynamics, thermodynamics, and magnetic fields, while n-body calculations handle gravitational interactions between planetesimals, planets, stars, and other cluster members. This multifaceted approach replicates the turbulent conditions prevalent in star-forming regions, where compressive shocks and gravitational tugs interplay in a complex dance. One of the primary findings from these simulations is that planetary ejections are relatively common outcomes, especially within the first few million years after formation. Gravitational interactions within multi-planet systems induce instabilities, and close encounters with sibling stars in the dense cluster environment can further disrupt planetary orbits. The chaotic nature of these interactions results in a spectrum of fates. Planets may settle into stable orbits, collide with other bodies, or be ejected entirely into interstellar space. The timing and mechanics of ejection depend on several factors. Simulations reveal that massive gas giants are often the primary candidates for ejection due to their gravitational influence in destabilizing the system. Additionally, the cluster's density matters. In more crowded regions, close stellar flybys are more frequent, increasing the ejection likelihood. These models also account for stellar feedback, such as radiation and winds, which influence the dispersion of gas and affect planetary migration and stability. As rogue planets are set free, simulations help map their trajectories and velocities. Some are slowly nudged away, while others are rapidly accelerated to high speeds, hurtling through the galaxy as interstellar castaways. Their velocities depend on the ejection mechanism, such as gravitational scattering within the planetary system or disruptive close encounters with other stars. Simulated rogue planets also reveal a diversity in their expected characteristics after ejection. Some retain thick atmospheres and internal heat generated during formation, providing a degree of sustained warmth despite the absence of a host star. Others rapidly cool and freeze, becoming dark, cold bodies wandering in the galactic void. These details are essential in predicting observational signatures and guiding searches. In addition to solitary wanderers, some simulations show the possibility of rogue planets carrying moons or debris, hinting at complex systems traveling alone. The dynamical stability of such satellite bodies under solitary conditions is a subject of ongoing research. Beyond ejection, simulations explore the later stages of a rogue planet's journey. Without the stabilizing gravity of a star, their orbits around the galactic center are shaped by the combined gravitational fields of the Milky Way's disk, bulge, halo, and dark matter distribution. Over billions of years, a rogue planet's path can be deflected by passing stars, molecular clouds, or tidal forces, influencing its velocity and trajectory through space. Simulations also model potential encounters between rogue planets and existing star systems. While rare on a cosmic scale, these close passages could result in gravitational captures or perturbations within planetary systems, possibly reintegrating rogue planets or causing disruptions, adding further intricacy to galactic dynamics. The insights from these simulations are profound, transforming our understanding from abstract hypotheses into quantitative narratives. They also inform observational strategies by helping to estimate the prevalence, velocity distributions, and thermal states of rogue planets, critical parameters for detection methods like microlensing and infrared surveys. Moreover, simulations provide test beds for exploring astrobiological implications, such as the prospects for subsurface oceans heated by residual internal energy or tidal interactions. They help in modeling how such environments might persist and evolve over cosmic timescales. In summary, simulating the journey of rogue planets bridges scales from the intimate environments of star nurseries to the grand galactic architecture. These models open a window onto the solitary odysseys of worlds without suns, enriching our cosmic perspective and setting the stage for understanding the diversity and destiny of the galaxy's most loneliest travelers. As we proceed, this foundation prepares us to categorize these diverse rogue worlds, the Rogue Planet Zoo, by examining their sizes, compositions, and origins, showcasing the rich tapestry of planetary types that populate the interstellar darkness. As we journey deeper into the realm of rogue planets, it becomes evident that these starless wanderers are not a monolithic group, but rather a diverse collection of worlds with varying sizes, compositions, and origins. Much like a zoological classification groups animals into categories based on shared characteristics, astronomers have begun organizing rogue planets into a cosmic zoo to better understand their nature and trace their histories. This classification is crucial for guiding observations, framing theoretical models, and exploring the broader implications of their existence. The first axis of classification is size, which broadly reflects mass and volume, two fundamental attributes shaped by formation processes and evolutionary histories. Rogue planets cover a wide spectrum, from sub-Earth mass bodies comparable in size to Mars, or even smaller, to gas giants exceeding the size of Jupiter. This size range overlaps with that of planets within star systems, suggesting that the processes that birth or eject these bodies produce a similar diversity. Smaller rogue planets, often rocky and terrestrial in nature, likely share characteristics with Earth-like planets, but exist without the stabilizing influence and warmth of a sun. These bodies might have formed in circumstellar disks, but were ejected before significant gas accretion or before acquiring substantial atmospheres. Alternatively, some may be remnants of collisions or the cores of disrupted larger planets. On the upper end are gas giant rogues, huge, often several times the mass of Jupiter, composed mainly of hydrogen and helium. These giants may have formed rapidly within their star's disk, accumulating thick gaseous envelopes before dynamical interactions ejected them into interstellar space. Their massive sizes contribute to longer retention of internal heat, influencing their detectability in infrared wavelengths. Composition forms the second dimension of classification and provides crucial clues about a rogue planet's origin and evolutionary path. Compositionally, rogue planets fall into broadly terrestrial, rocky, icy, or gas giant categories. Terrestrial rogue planets tend to be dense, composed primarily of silicates and metals, similar to Mars or Earth. Icy rogues contain significant quantities of volatile ices such as water, ammonia, and methane, potentially forming thick ice layers beneath their surfaces. Gas giants feature extensive hydrogen and helium atmospheres enveloping solid cores, akin to Jupiter and Saturn in our solar system. The composition not only relates to a planet's mass and size, but also its thermal and geological state. For example, gas giants can retain more internal heat, affecting their infrared brightness and atmospheric dynamics, whereas smaller rocky planets may cool quickly and have geologically inactive surfaces, unless tidal or radioactive heating is present. Moreover, rogue planets might carry exotic atmospheres or surface states, depending on their formation environment and history. Some may harbor thick, hydrogen-rich atmospheres if ejected early, while others may have lost volatile components due to cosmic radiation exposure in interstellar space. Origins, the third crucial classification factor, delve into the narrative of how a rogue planet came to be. Astronomers generally distinguish between two principal origins: ejection from bound planetary systems and in situ formation as isolated objects. Rogue planets formed and then cast away from their stellar families typically exhibit characteristics reflecting their progenitor system, chemical signatures, remnants of atmospheres, or satellite companions. Their histories are often intertwined with the violent dynamics of their birthplaces, including gravitational scattering or stellar encounters that propelled them into solitary journeys. In contrast, some rogue planets may form directly from gravitational collapse of molecular cloud fragments, akin to the birth of brown dwarfs and stars, but on smaller scales. This starless formation route tends to create objects with compositions reflective of their natal clouds and less influenced by protoplanetary disk processes. Distinguishing between these origins is challenging, especially when observational data are limited. Nevertheless, emerging techniques, including detailed spectroscopy and kinematic studies, help piece together formation histories. For example, young, isolated objects with characteristics analogous to gas giants but formed in star-forming regions suggest in situ origins, while older, field rogue planets may hint at ejection scenarios. In addition to these primary categories, astronomers also recognize subtypes influenced by factors such as age, thermal evolution, atmospheric composition, and whether the rogue planet carries moons or rings. Some rogue planets might be fossil remnants of planetary system evolution, bearing scars of their ejection events, while others are relatively youthful, retaining signs of recent formation. Understanding the Rogue Planet Zoo enriches not just our cataloging efforts, but also guides the search for these elusive objects. Different classes require tailored observational strategies. For example, infrared surveys are more effective at spotting warm, massive rogue planets, while microlensing techniques can detect a broad mass spectrum. This classification also fosters deeper inquiries, such as the astrobiological potential of rogue planets based on their size and composition, or the statistical prevalence of origins pathways, questions that intertwine planetary science with galactic dynamics and cosmology. In essence, the Rogue Planet Zoo is a testament to nature's creativity and complexity. These starless travelers, diverse in form and origin, embody the dynamic and interconnected processes shaping our galaxy. By categorizing and studying them, we not only broaden our cosmic inventory, but also gain insights into the life cycles of planets, the forces shaping planetary systems, and the hidden depths of our interstellar neighborhood. With this understanding of rogue planet diversity, we can now turn to explore one of the most extraordinary facets of these worlds: their existence in the cold and darkness of space, environments vastly different from the sunlit realms we are familiar with. Let us delve into the extreme conditions and mysteries of life without a sun. Life on Earth, and indeed throughout much of our solar system, owes its existence and sustainability to the steady and generous energy supplied by our sun. Its warmth drives climate, powers photosynthesis, and moderates the delicate balance that nurtures countless ecosystems. But what becomes of a world when severed from this vital energy source? Rogue planets, wandering through the vast sunless reaches of interstellar space, embody this profound departure from familiar planetary environments. Exploring their extreme and often hostile conditions lays bare the very limits of planetary habitability and challenges our assumptions about where life might exist. At first glance, rogue planets seem forbidding worlds of perpetual darkness and freezing cold. Devoid of the radiant glow and heat of a host star, their surfaces are bombarded by the chilling vacuum of space. Temperatures are expected to plummet precipitously, reaching a few degrees above absolute zero in the absence of internal heat or atmospheric insulation. Such cold would freeze any surface water solid, rendering the planet's exterior an alien desolation far removed from the temperate zones known to us. Yet, these worlds are not simply ice-cold and inert. Internal heat sources, although weak compared to stellar energy, can play crucial roles. Residual heat from planetary formation, radioactive decay within the planet's core, and gravitational contraction generate thermal energy that may sustain subsurface warmth long after their stellar warmth is extinguished. In some cases, this internal energy could maintain liquid water oceans beneath thick layers of ice, creating hidden aquatic realms cloaked in darkness. The absence of sunlight means that surface photochemistry, the chemical reactions driven by light, is extraordinarily limited. Atmospheric and surface compositions on rogue planets would owe their characteristics to other processes, such as volcanic outgassing, internal chemistry, and cosmic ray interactions. However, without the shielding magnetic fields sometimes generated by a star's interaction, rogue planets might have less protection from cosmic radiation, subjecting their surfaces and atmospheres to harsh space weathering. Atmospheres on rogue planets, if present, would behave differently than on illuminated planets. Without stellar energy to drive weather systems, atmospheric dynamics may be sluggish or dominated by internal heat. Thick atmospheres could act as insulating blankets, trapping geothermal warmth and moderating surface temperatures. Hydrogen-rich atmospheres, especially on larger rogue planets, may retain heat effectively, prolonging habitable niches. In such extreme cold and darkness, conventional photosynthetic life as we know it seems unlikely. However, the possibility of chemosynthetic life, organisms deriving energy from chemical reactions rather than light, raises intriguing astrobiological prospects. Subsurface oceans warmed by geothermal activity could harbor microbial ecosystems analogous to those found around Earth's deep-sea hydrothermal vents, thriving on chemical gradients independent of sunlight. The lack of a sun also affects geological activity and planetary magnetism. Geothermal heat may drive tectonic processes beneath icy crusts, generating environments suitable for life and maintaining magnetic fields that could shield the interior from cosmic ionizing radiation. Loss of magnetic protection, however, could expose surfaces to sterilizing radiation, confining potential habitability to subterranean refuges. Moreover, rogue planets might host exotic forms of chemistry and geophysics due to their isolation and unique conditions. Atmospheric composition might include heavier gases or volatile ices, uncommon on planets warmed by stars. The stability of such atmospheres over cosmic timescales, influenced by surface temperature, pressure, and escape processes, remains a subject of research. Despite the bleakness of lightless existence, the resilience and adaptability of life on Earth suggest that worlds beyond suns may hold surprises. The study of extremophiles thriving in Earth's most inhospitable niches fuels speculation that life, if it emerges, could persist even in the dark, cold domains of rogue planets. From an observational standpoint, extreme environments influence how rogue planets can be detected. Their intrinsic faintness in visible light necessitates searches in infrared wavelengths, targeting the weak thermal emissions generated by internal heat. Surface and atmospheric characteristics shaped by these environments also affect spectral signatures, measurable by powerful instruments. In sum, life without a sun presents one of the most profound environmental challenges imaginable, making rogue planets some of the galaxy's most extreme worlds. Their harsh conditions press against the boundaries of habitability, inviting us to expand our definitions of life's domains and the environments in which it might thrive. As we further investigate the potential for warmth and energy within these cold wanderers, we turn next to explore the internal heat sources and mechanisms that might sustain life-supporting conditions, even in the absence of stellar light. A journey into the heart of heat in the cosmic void. Rogue planets traverse the immense darkness of interstellar space, devoid of any nearby star to provide warmth or light. At first glance, these planets appear destined to be frozen, lifeless rocks, locked in an eternal cosmic winter. Yet, beneath their frigid exteriors, a variety of internal heat sources can illuminate the possibility of active geology, complex atmospheres, and potentially even habitats capable of supporting life. Understanding the origins and sustainability of this internal warmth is vital to comprehending the nature and evolution of rogue planets as they float silently through the galaxy. One primary source of internal heat in any planetary body is the residual thermal energy left over from its formation. When a planet forms through the accretion of gas and dust, gravitational energy converts into heat as materials collide and compress, raising internal temperatures significantly. For rogue planets, this primordial heat can persist for millions or even billions of years, slowly radiating away into the void. Large, massive rogue planets, such as gas giants, retain this heat longer due to their insulating atmospheres and deep, thick layers of hydrogen and helium, whereas smaller, rocky rogue planets lose heat more rapidly, Radioactive decay within a planet's interior also produces heat. Naturally occurring radioactive elements such as uranium, thorium, and potassium continuously emit radiation as they decay into more stable forms. This process releases energy in the form of heat that can maintain geological activity, such as mantle convection and volcanism, particularly in terrestrial rogue planets rich in heavy elements. On Earth, radioactive decay is a significant contributor to the planet's internal heat, powering plate tectonics and maintaining the magnetic field, processes essential to the planet's habitability. Gravitational contraction, known as Kelvin-Helmholtz contraction, is another enduring heat source, especially for gas giants and massive planets. As the planet slowly contracts over time due to its own gravity, the compression under immense pressure converts gravitational potential energy into thermal energy, heating the planet's deep interior. This mechanism can sustain a warm core long after the loss of primordial heat. Tidal heating, a process often discussed for moons orbiting giant planets, could theoretically apply to rogue planets under certain conditions. If a rogue planet carries natural satellites or passes near massive objects like stars or other planets, tidal forces would flex its interior, generating frictional heating. While the absence of a central star removes many tidal heating scenarios, transient encounters in dense star clusters or with passing stars might impart temporary tidal stresses. Geochemical reactions within a planet's interior provide additional heat sources. Certain chemical processes, such as serpentinization, the reaction of water with mantle rocks, can release heat and even free hydrogen, which may serve as an energy source for microbial life. These processes require the presence of liquid water and reactive minerals, conditions possibly met in the subsurface layers of some rogue planets. Another fascinating possibility is the role of exotic insulating atmospheres. Thick envelopes composed of hydrogen or other greenhouse gases can trap internal heat, dramatically affecting the planet's surface or near-surface temperatures. In the absence of solar heating, such greenhouse effects could mean the difference between a planet's surface being a frozen wasteland or selectively warm enough in pockets to sustain liquid water beneath icy crusts. Furthermore, cosmic rays and interstellar radiation might induce weak ionization and chemical reactions in rogue planet atmospheres, possibly contributing minor heat, but more importantly affecting atmospheric chemistry and dynamics. Quantifying these internal energy sources is not mere theoretical pondering. It has direct implications for the detectability of rogue planets. Internal heat manifests as thermal infrared emissions, faint glows detectable by sensitive space telescopes. Larger, warmer rogue planets are more observable due to retained internal heat, guiding astronomers to targets and refining population estimates. The persistence and interplay of these heat sources paint a picture of rogue planets not as frozen, inert stones, but as dynamic, evolving worlds with the capacity for geological and potentially biological complexity. Their internal warmth challenges our conception of habitability, demonstrating that energy necessary for certain life processes can arise from within, independent of a host star's energy. Understanding heat in the void, therefore, unfolds a crucial chapter in comprehending the viability and diversity of rogue planets. It opens pathways to considering subsurface oceans, geothermal habitats, and energy cycles that might sustain life in the universe's loneliest regions. Building upon this understanding, we next explore the astrobiological potential lurking beneath the surfaces of these starless worlds, the subsurface oceans and geothermal havens that may foster life in the darkness. In the vast, frigid expanses of interstellar space, where rogue planets drift without the nurturing warmth of a sun, the possibility of habitable environments might seem dim at best. Yet, beneath the frozen surfaces of these starless worlds, lies a tantalizing prospect: subsurface oceans and geothermal havens that could harbor conditions suitable for life, extending the frontiers of astrobiology far beyond the traditional concept of habitable zones. The idea of subsurface oceans on rogue planets draws inspiration from moons within our own solar system, such as Jupiter's Europa and Saturn's Enceladus, which hide vast liquid water oceans beneath icy crusts. Despite their distance from the Sun and surface temperatures plunging far below freezing, these worlds maintain liquid water thanks to internal heating mechanisms. This concept naturally extends to rogue planets, which, though deprived of stellar energy, might possess sufficient internal warmth to sustain subsurface liquid reservoirs. Central to sustaining such oceans is the planet's internal heat, derived mainly from radioactive decay of elements within the mantle and core, residual heat from formation, and potentially tidal heating if the planet harbors one or more moons. Unlike the surface, which would be exposed to the cold vacuum of space, the subsurface ocean could be insulated beneath thick layers of ice, preserving its liquid state over geological timescales. This layered structure offers a protective environment that shields potential biotic niches from harsh cosmic radiation and temperature extremes. Geothermal activity, driven by the planet's internal heat, plays a critical role in maintaining chemical cycles necessary for life. Hydrothermal vents, fissures on the ocean floor where heat and mineral-rich fluids emerge, could provide energy and nutrients analogous to those fueling Earth's deep-sea ecosystems. The presence of such environments would provide a metabolic foundation for chemosynthetic life, organisms capable of harvesting chemical energy from minerals rather than sunlight. The composition of the subsurface ocean itself would influence its habitability. Liquid water, a solvent essential for life as we know it, might be enriched with salts and other dissolved minerals that support prebiotic chemistry and biological processes. Thickness of the ice shell, pressure conditions, and possible exchange mechanisms between ocean and surface determine the complexity and sustainability of these habitats. Moreover, certain rogue planets might possess atmospheres thick enough to provide additional insulation, slowing heat loss and potentially supporting more complex surface or near-surface environments. The atmospheres could also facilitate the cycling of gases essential for biological metabolism, such as methane or hydrogen, further enriching the habitable potential. Astrobiologists also speculate that life on such worlds, if it exists, could be microbial or even more complex, adapted to the perpetual darkness and reliance on chemical energy sources. While this remains purely theoretical, recent studies of extremophiles on Earth, organisms surviving without sunlight in deep oceanic vents or subglacial lakes, demonstrate life's remarkable resilience and adaptability. Challenges remain in understanding the longevity of these subsurface habitats, especially considering the eventual cooling of the planet's interior over billions of years. However, some models suggest that geothermal heat may persist long enough to allow life to emerge and persist. From an observational perspective, detecting subsurface oceans or geological activity on rogue planets is difficult with current technology. Indirect methods include analyzing thermal emissions indicative of internal heat and searching for chemical signatures in atmospheres or plumes, if present. Overall, the concept of subsurface oceans and geothermal havens on rogue planets expands our conception of habitable real estate in the cosmos. It invites us to imagine life in forms and places far removed from the sunlit worlds we know, underscoring the vast potential of the universe to foster biology under even the darkest, coldest conditions. Building upon this astrobiological potential, the next chapter examines speculative life forms that might inhabit these lonely worlds, exploring the fascinating realm of creatures of the darkness, the possibilities and limits of life beneath alien ice. As we cast our minds toward the starless realms of rogue planets, the question inevitably arises: could life exist in such profoundly dark, cold, and isolated environments? Without the nurturing glow of a sun, these wandering worlds seem inhospitable, yet the resilience of life on Earth and the breadth of astrobiological speculation invite us to entertain speculative possibilities of creatures thriving in the darkness. Exploring life on rogue planets stretches the boundaries of biology, chemistry, and imagination, challenging us to rethink what forms life might take, how it might obtain energy, and where it might persist in the vast cosmic night. Life on Earth demonstrates remarkable adaptability, surviving and flourishing in environments once thought barren or extreme. From deep ocean hydrothermal vents, where sunlight never penetrates, to subglacial lakes miles beneath Antarctic ice, organisms harness chemical energy sources to thrive. These extremophiles provide a natural blueprint for conceiving life on rogue planets. Organisms that do not depend on sunlight, but instead utilize chemical and geothermal energy to power metabolism and reproduction. On rogue planets, the absence of photosynthesis forces speculation toward chemosynthetic life forms. Such life would exploit redox reactions involving chemical gradients between minerals and compounds, analogous to microbes around Earth's deep-sea vents that oxidize hydrogen sulfide or methane. Internal planetary heat might maintain liquid water oceans beneath icy shells, creating stable habitats shielded from cosmic radiation and the brutal cosmic cold. One possibility is that life on rogue planets could resemble microbial mats or biofilms, communities of simple, single-celled organisms forming intricate ecosystems within subsurface oceans. These life forms might rely on chemically rich hydrothermal vents or volcanic activity, exploiting the energy released by geochemical processes. The biological machinery of such organisms might be based on universal biochemistries known on Earth, or possibly alternative molecular structures adapted to physicochemical conditions unique to rogue worlds. Beyond microbe-like life, speculative evolution might yield more complex creatures. In subsurface oceans, multicellular organisms adapted to turbulence-free environments and perpetual darkness could evolve. Their sensory apparatus, if any, might rely on chemical gradients or mechanoreception rather than eyesight. Such life forms could exploit nutrient cycles driven by geothermal activity, inhabiting ecosystems bound by energy sources fundamentally different from sunlight. Rogue planets with substantial atmospheres might host surface or near-surface environments somewhat less alien. Thick, insulating atmospheres could maintain temperatures soft enough to permit liquid oceans, or even atmospheres dense with reactive gases, potential energy sources for life. In rare cases, weather systems powered by internal heat might develop, offering analogs to Earth's ecosystems, but wholly sustained by internal planetary energy. The dark universe posits intriguing possibilities for entirely novel biochemistries. Low temperatures and the presence of exotic ices or solvents, such as ammonia or methane, might support atypical metabolic pathways and molecular structures. Life within these environments might bear little resemblance to Earth-based forms, yet fulfill equivalent ecological roles. However, this speculative panorama must acknowledge challenges. The energetic constraints of these isolated systems limit biological complexity. The slow cycling of nutrients, extreme coldness, and high radiation levels present formidable obstacles. Nonetheless, life's persistence under Earth's harshest conditions suggests that under the right conditions, life, or life's precursors, might endure even here. Moreover, some hypotheses posit that rogue planets might serve as cosmic life reservoirs, capable of transporting biological material between star systems through panspermia mechanisms. This prospect links biological speculation with galactic dynamics and the age-old question of life's distribution in the cosmos. While the existence of life on rogue planets remains purely hypothetical, studying these speculative possibilities inspires interdisciplinary research, bridging astronomy, planetary science, biology, and chemistry. As telescopes and probes advance, they may one day reveal biosignatures or environmental clues hinting at life in the cosmic darkness. In contemplating creatures of the darkness, we expand our understanding of life's potential, illuminating the universe's creative capacity and humbling our perspectives on existence. As our exploration continues, we next turn to the influence these wandering worlds might exert on other planetary systems, examining the cosmic interplay of interruptions, collisions, and disruptions they may cause on their lone voyages among the stars. The galaxy is a vast and dynamic environment where the paths of stars and their planetary systems weave complex stories of motion and interaction. Amid this cosmic choreography, rogue planets, worlds unmoored from any star's gravitational embrace, drift through interstellar space, silent and often unseen. While their lonely journeys suggest isolation, these nomads can, on occasion, traverse the domains of established planetary systems, giving rise to gravitational disturbances that profoundly affect the architecture and stability of those systems. In this section, we delve into the multifaceted impacts rogue planets may exert on star-bound planetary systems, from gentle interruptions to catastrophic collisions and gravitational disruptions. When a rogue planet passes close to a star system, its gravitational field acts as a potent disruptor, albeit typically fleeting. The strength of its influence depends on several factors, such as its mass, velocity, trajectory, and the configuration of the planetary system it encounters. Even a relatively small rogue planet can induce measurable perturbations in the orbits of planets, asteroid belts, or comet clouds through tidal forces and gravitational resonances. One of the primary consequences of such encounters is orbital disruption. A close passage can nudge planets into more eccentric or inclined orbits, potentially destabilizing orbital resonances that maintain the system's long-term balance. Such perturbations may excite planets into crossing orbits, increasing the risk of collisions or ejections within the host system. Over time, a single rogue planet's flyby can cascade into a reshaped planetary architecture, possibly spawning new dynamical equilibria or, conversely, leading to gradual instability. In more extreme scenarios, a rogue planet passing sufficiently close to a star could be captured gravitationally, becoming a new member of that star's planetary family. Though rare, such captures could implant previously starless worlds as permanent satellites, dramatically altering both the rogue planet's destiny and the system's composition. If captured, these planets may follow highly elliptical orbits initially, gradually circularizing over extended timescales. Alternatively, rogue planets may collide directly with bodies in a planetary system, planets, moons, or asteroids, if trajectories align. Such collisions, though exceedingly rare on human timescales, would be cataclysmic, generating enormous energy release, ejecting debris, and possibly triggering secondary impacts or system-wide perturbations. Collisions might also explain certain anomalous properties of planets, including unusual spin rates, crustal compositions, or the presence of debris disks resulting from recent impacts. Beyond planets, rogue flybys may stir up distant comet reservoirs, such as the hypothetical Oort cloud, sending comets toward inner star systems and increasing bombardment rates. This process could influence planetary surface evolution, atmospheric chemistry, and potential biotic processes by delivering volatiles or causing impact winters. In this way, rogue planets act as cosmic agitators, influencing the long-term evolution of planetary environments indirectly. The cumulative effects of such encounters depend on the frequency of rogue planet passages near star systems. While the sheer scale of the galaxy suggests close encounters are rare in any given system, over billions of years and across billions of stars, the statistical significance becomes meaningful. Dense stellar regions or young clusters increase encounter probabilities, intensifying dynamical interactions early in star system histories. Astrophysical simulations help illuminate these phenomena by modeling scenarios of rogue planet flybys, capture probabilities, collision frequencies, and their impacts on system stability. These simulations reveal that rogue planet encounters, though infrequent, can act as catalysts for dramatic changes in planetary systems, including triggering planetary migrations, destabilizing orbits, or even causing the ejection of native planets, adding to the rogue planet population. Moreover, the exchange of material facilitated by such interactions raises fascinating possibilities for panspermia, the transfer of life or its precursors between worlds. Collisions or close passes might sling surface material, harboring microbes or organics, from one planet to another or even onto a rogue planet, potentially seeding life in otherwise inhospitable realms. From an observational perspective, identifying evidence of past or ongoing rogue planet interactions is challenging, but not impossible. Unusual planetary orbits, sudden changes in debris disks, or anomalous impact crater patterns may hint at such events. Future surveys and missions will enhance our abilities to detect these subtle, yet profound signs. In summary, rogue planets, while often solitary travelers, have the potential to profoundly influence other planetary systems through gravitational disruptions, collisions, and material exchange. Their silent wanderings occasionally echo as dynamic imprints on the evolutionary tapestry of star systems, underscoring the interconnected complexity of our galaxy's planetary population. Having explored these cosmic interactions, we now turn our attention to the ongoing quest to detect these elusive worlds through the analysis of subtle signals, ghosts in the data, that future telescopes seek to unveil. Detecting rogue planets presents one of the most formidable challenges in modern astronomy, akin to searching for ghosts hidden in the vast cosmic expanse. These elusive worlds emit little to no visible light and do not orbit stars, which eliminates many traditional planet detection methods reliant on stellar illumination or signal. Yet, despite these difficulties, astronomers have developed innovative approaches and are eagerly anticipating future telescopes that promise to transform our capacity to identify and characterize these shadowy denizens of interstellar space. Currently, the primary tool for identifying rogue planets is gravitational microlensing, a method that captures transient brightenings of distant background stars caused by the gravitational field of a rogue planet acting as a lens. While microlensing has been extraordinarily successful in unveiling populations of rogue planet candidates, its limitations are well known. Microlensing events are unpredictable, brief, and require continuous wide-field monitoring of crowded stellar regions. Crucially, once an event fades, the rogue planet is lost from view, making detailed follow-up studies difficult. Beyond microlensing, direct imaging in the infrared spectrum offers a promising avenue. Rogue planets, particularly those that are young and massive, retain internal heat from their formation and contraction, emitting faint infrared radiation detectable by sensitive telescopes. Space-based observatories such as the James Webb Space Telescope, JWST, and ground-based facilities equipped with advanced adaptive optics are at the forefront of pushing detection limits, seeking the faint thermal signatures of these cold wanderers. Future telescopes are poised to revolutionize this search. The Nancy Grace Roman Space Telescope, slated for launch in the mid-2020s, will conduct a wide-field microlensing survey with unprecedented sensitivity and cadence. Roman's survey will detect thousands of microlensing events, including those caused by free-floating planets down to Earth mass, enabling a statistical census far surpassing current capabilities. This will provide crucial insights into the frequency, distribution, and masses of rogue planets throughout the Milky Way. Meanwhile, the Vera C. Rubin Observatory, previously known as LSST, with its wide-field deep imaging capabilities, will scan the sky repeatedly over a decade. Its ability to detect moving objects with faint infrared and optical signatures means it might catch rogue planets passing relatively close to the solar neighborhood. Rubin's large data sets, combined with sophisticated data mining and machine learning techniques, will help identify subtle transient events or moving point sources consistent with rogue planetary mass objects. On the horizon is the European Extremely Large Telescope, EELT, set to deliver unparalleled resolution and sensitivity. Equipped with state-of-the-art spectrometers, EELT will potentially study rogue planet candidates directly, probing their atmospheres and thermal properties, which could illuminate their formation histories and compositions. Another intriguing future prospect is the use of astrometry, the precise measurement of stellar positions and motions, to detect the gravitational influence of passing rogue planets on background stars. ESA's Gaia mission is leading the way in measuring the positions of over 1 billion stars with unprecedented accuracy. While Gaia's primary focus is on stars, its data might reveal tiny, transient perturbations induced by massive rogue planets traversing near line-of-sight paths, opening a new detection window. Challenges remain. Differentiating rogue planets from other objects such as brown dwarfs, isolated low-mass stars, or background galaxies requires careful spectral and kinematic analysis. The faintness, rarity of events, and complexity of signal processing all demand sophisticated algorithms and sustained observational campaigns. Efforts to combine multiple detection techniques, such as microlensing, direct imaging, and astrometry, alongside advancing computational models, will refine candidate lists and push observational frontiers. The integration of artificial intelligence and machine learning in massive cosmological data sets will be critical to pinpoint rogue planet signatures hidden amid overwhelming background noise. In essence, rogue planets have transformed from theoretical curiosities into plausible and detectable members of the galactic menagerie. The coming decades, buoyed by next-generation telescopes and computational advances, promise to illuminate these ghosts in the data, bringing into focus the loneliest worlds and revealing new chapters in the story of planetary diversity and cosmic evolution. As our eyes grow sharper and our data deeper, the hunt for rogue planets intensifies, beckoning us toward new discoveries and deeper understanding. An ongoing journey into the silent wilderness of the galaxy. Rogue planets, those enigmatic worlds adrift in the cosmic blackness without a guiding sun, have long captured the imagination not only of scientists, but also of storytellers and creators, stepping beyond the boundaries of scientific discourse into the realms of myth, literature, and popular culture. Their very nature, as solitary wanderers of the galaxy, orbiting no star and bathed only in the faint glow of distant stars, resonates deeply with themes of isolation, mystery, and the unknown, fueling a rich cultural presence that intertwines with humanity's enduring fascination with the cosmos. In science fiction, rogue planets have been fertile grounds for speculative storytelling, serving as settings, plot devices, or metaphors for existential isolation and discovery. Early portrayals often depicted these starless worlds as dark, inhospitable voids, lonely outposts at the edge of known space, embodying the ultimate frontier to be explored or feared. The lack of a sun's warmth became a symbol of desolation and challenge, where intrepid explorers confront extremes of cold and darkness, testing human ingenuity and survival. Notable in literature is the concept of rogue planets as mysterious objects whose unusual trajectories intersect with inhabited systems, threatening extinction or offering sanctuary. This motif appears in numerous television series, films, and novels, from the chilling isolation evoked in deep space dramas to the awe-inspiring marvels of secretively harboring advanced life under thick ice shells. Beyond the realm of fiction, rogue planets intrigue popular science media and documentaries, where their existence challenges the conventional understanding of planetary systems. They evoke wonder and curiosity, inspiring awe at the diversity and dynamism of the cosmos. The scientific narrative surrounding rogue planets fuels educational content, public talks, and outreach programs that captivate audiences with possibilities for life beyond normal constraints, amplifying humanity's cosmic perspective. Their cultural resonance extends into symbolic and philosophical domains. The image of a planet cast out into the void taps into universal themes of exile, loneliness, and wandering, motifs deeply ingrained in human storytelling and mythic traditions. Rogue planets metaphorically echo human experiences of isolation and the search for belonging, illustrating how cosmic phenomena can mirror inner emotional landscapes. Artists and visual creators have embraced rogue planets as inspirations for striking imagery. Worlds shrouded in perpetual night, illuminated only by ethereal glows. Scenes featuring frozen landscapes lit by distant stars, or auroras born of exotic atmospheres, and surreal, minimalist visions of solitude juxtaposed against the vastness of space. These representations evoke emotional responses and creative reflections on humanity's place in the universe. In gaming and interactive media, rogue planets often function as compelling backdrops for exploration and survival scenarios. Their unpredictable, forbidding nature challenges players to adapt and discover, weaving scientific notions with imaginative gameplay. Such representations engage players in speculative inquiry, blending education with entertainment. Moreover, philosophical and theological discussions sometimes invoke rogue planets in contemplating the boundaries of life, habitability, and cosmic significance. They become focal points for questioning the uniqueness of Earth and the diversity of possible life-bearing environments, prompting reflection on our relationship with the cosmos. The interplay between scientific discovery and cultural imagination creates a feedback loop. As astronomy reveals more about rogue planets, their numbers, nature, and environments, public fascination deepens, inspiring new stories, art, and inquiry. Conversely, cultural portrayals influence the narratives and questions scientists pursue, shaping the popular conceptual frameworks through which the public understands complex celestial phenomena. As we continue to explore and understand these lonely worlds, their cultural imprint grows, serving as potent symbols of cosmic mystery and human curiosity. Rogue planets remind us that the universe is not only astronomically diverse, but also endlessly evocative, prompting us both to explore the stars and to reckon with our own existential journeys. From this rich cultural tapestry, we now turn to the more scientific and speculative notion of rogue planets as cosmic hitchhikers, conceivable agents of interstellar panspermia capable of transporting life between star systems. This duality of grounded science and expansive imagination continues to make rogue planets endlessly fascinating subjects of study and storytelling alike. The vastness of interstellar space is often portrayed as an insurmountable barrier, a dark gulf separating star systems by unimaginable distances and hostile conditions. Yet, within this cosmic ocean, rogue planets drift, unmoored worlds wandering the galaxy's depths, carrying with them not only geological secrets, but perhaps something even more profound: the seeds of life. This speculation lies at the heart of one of the most captivating ideas in astrobiology and planetary science: panspermia, the hypothesis that life, or its precursors, can be transported between star systems, potentially spreading biology across the galaxy. Rogue planets, as cosmic hitchhikers, may serve as vehicles for this interstellar transfer, bridging worlds and challenging our notions of life's origin and dispersal. Panspermia has long fascinated scientists and philosophers alike. On Earth, the discovery that certain microorganisms withstand extreme environments, from deep-sea vents to the vacuum and radiation of space, has bolstered the idea that life's building blocks are remarkably resilient. This raises the possibility that life could survive journeys across interplanetary and even interstellar distances, provided the right carriers and conditions. Rogue planets, drifting alone, yet massive enough to sustain subsurface environments, emerge as intriguing candidates for such carriers. The concept rests on several key premises. First, if life exists on a planet bound to a star, catastrophic events such as large impacts, supernova blasts, or stellar mass loss could eject fragments of that planet's crust or even parts of its biosphere into space. Some of these ejecta, rocky debris harboring microorganisms, could escape their parent star's gravity. In scenarios where a planet or fragment is propelled into interstellar space, it might become a rogue body, traveling through the galaxy as a cosmic lifeboat. Second, rogue planets themselves might provide a protective environment for life during these interstellar voyages. Thick ice shells or dense atmospheres could shield dormant life forms or spores from cosmic radiation and the deep cold of space. Subsurface oceans warmed by internal geothermal heat might sustain microbial communities for extended periods, preserving life even in isolation from sunlight. Third, over immense timescales, tens of millions to billions of years, these rogue planets could pass near or be captured by other star systems. During such encounters or collisions, material potentially carrying life might be exchanged, delivering viable organisms or organic compounds to new worlds and igniting fresh evolutionary trajectories. This notion of rogue planets as cosmic hitchhikers fundamentally alters perspectives on planetary habitability and the origin of life. Instead of life arising independently on each world, it might spread as an interstellar diaspora, connecting the biospheres of myriad star systems. The implications ripple outward, affecting interpretations of planetary biology, the frequency and distribution of life in the universe, and even the search for extraterrestrial intelligence. Astrophysical models simulate these processes, revealing plausible pathways by which ejecta could travel, bound to or from rogue planets. Although the likelihood of intact life surviving such harsh journeys remains debated, experiments demonstrate resilience of extremophiles and spores, lending credence to possibilities once considered remote. Observationally, while detecting life or its biological markers on rogue planets is beyond current capability, forthcoming telescopes equipped to study exoplanet atmospheres might seek chemical biosignatures indicative of life-supporting conditions on both bound and free-floating planets. Discoveries along these lines would have profound consequences for panspermia theories. Moreover, the study of meteoritic material and cosmic dust impacting Earth sheds light on the exchange of organic compounds across planetary boundaries within our solar system, a microcosmic example of panspermia-like processes. Extending these concepts to interstellar scales naturally invites the role of rogue planets. In contemplating rogue planets as cosmic hitchhikers, we embrace a vision of the galaxy as an interconnected web, a biosphere not limited by solar boundaries but shared via wandering worlds and molecular travelers. This view enriches the poetic and scientific narrative of life's persistence and ubiquity in the cosmos. Expanding upon the possible habitation of these starless worlds, our exploration next leads us to consider the proximity of rogue planets to our own solar system. Could any be lurking nearby, awaiting discovery in the darkness just beyond our celestial neighborhood? Our solar system, a vibrant family of the sun, planets, moons, asteroids, and comets, occupies just a tiny corner of the vast Milky Way galaxy. Yet, beyond the acknowledged boundaries of this system, might lurk unseen wanderers, rogue planets drifting silently in the darkness, devoid of stellar companionship and eluding detection. The possibility that such hidden rogue planets exist near our own cosmic neighborhood has profound implications for our understanding of the local galactic environment, planetary system evolution, and even the stability and history of our solar system. The search for hidden rogue planets close to the Sun is both tantalizing and challenging. By their very nature, rogue planets do not emit visible light as stars do, and do not reflect sunlight as orbiting planets do, making them extremely faint and difficult to detect using traditional optical telescopes. Moreover, if a rogue planet resides within a few light years, yet remains cold and dark, it might be almost invisible against the backdrop of space. Our current observational capabilities have limitations in identifying such dim, isolated objects, especially if their mass is closer to Earth's or smaller. Despite these obstacles, several lines of inquiry suggest that some undetected massive objects could be lurking nearby. Large-scale infrared sky surveys, such as those conducted by NASA's Wide Field Infrared Survey Explorer, WISE, have scanned vast portions of the sky with great sensitivity to cool objects, including brown dwarfs and planetary mass bodies. WISE has discovered several nearby brown dwarfs, revealing the presence of numerous faint objects in our neighborhood, but so far no definitive rogue planets within a few parsecs have been confirmed. Nevertheless, non-detections do not preclude the existence of elusive rogue planets, especially those with masses closer to Earth or Mars and cooler temperatures. Smaller bodies radiate even less heat and can escape detection with even the best infrared surveys available to date. Additionally, objects located in regions of the sky obscured by galactic dust or in areas insufficiently covered might remain hidden. Theoretical models add another perspective. Simulations of star formation and planetary system dynamics predict that rogue planets should be abundant throughout the galaxy, with some passing near the solar neighborhood at any given time. The gravitational influence of nearby massive rogue planets could, in theory, subtly perturb objects in the outer reaches of the solar system, such as the hypothesized Oort cloud or distant trans-Neptunian objects. Such perturbations could explain anomalous orbital patterns observed in some distant solar system bodies, fueling speculations about the presence of unseen massive objects, although definitive proof remains elusive. Further clues come from studies of comet trajectories and their apparent sources. If a rogue planet were passing near the solar system, its gravity might redirect comets or send showers of icy bodies toward the inner solar system. While no direct associations have been established, these hypotheses motivate continued monitoring and analysis. The growing deployment of powerful observatories and advances in astrometric precision promise to sharpen our search. The European Space Agency's Gaia mission has been mapping the positions and motions of over 1 billion stars with exquisite accuracy. Though primarily focused on stars, Gaia's data could reveal subtle gravitational influences from nearby massive but dark objects, potentially identifying candidate rogue planets near the Sun. New facilities like the Vera C. Rubin Observatory will conduct wide, deep, and repeated surveys covering the entire visible sky, improving the chances of discovering faint, fast-moving objects that might be rogue planets wandering close by. In essence, while no rogue planet has yet been confirmed in our immediate cosmic backyard, the possibility remains compelling and cannot be dismissed. Ongoing surveys, combined with sophisticated data analysis, may soon reveal these hidden wanderers, changing our conception of the solar neighborhood and the dynamic processes that mold planetary systems. As we uncover these mysteries lurking near us, the prospect of interstellar travel and exploration becomes all the more enticing. We now turn to imagine what an interstellar journey to a rogue planet might entail. What challenges would face such a voyage, and what wonders might await in these lonely but captivating worlds. Embarking on a journey to a rogue planet, a solitary world adrift in the vast interstellar darkness, represents one of the most awe-inspiring and daunting prospects humanity could ever envision. Unlike journeys to planets orbiting our Sun, visiting a rogue planet involves traversing light-years of empty space to reach an environment utterly alien, one without a sun, cloaked in perpetual darkness and cold, and governed by its own internal forces. Charting such an interstellar expedition compels us to consider a multitude of scientific, technical, and existential challenges, as well as the profound discoveries that could await such an unprecedented voyage. The first and most obvious challenge is the sheer distance. Rogue planets roam the galaxy far beyond the confines of traditional planetary systems, with the closest known stars already several light-years away. According to current astronomical surveys, it is plausible that a few rogue planets may drift within a few light-years of our solar system, but the exact distances, locations, and properties remain uncertain. Even reaching such a relatively close rogue world would require technology far beyond our current spacecraft capabilities, demanding propulsion systems capable of sustained, high-velocity travel over decades or centuries. Voyaging to a rogue planet raises questions about propulsion. Chemical rockets, like those used for lunar or Mars missions, are insufficient for interstellar travel. Advanced propulsion concepts, such as nuclear thermal or nuclear electric drives, light sails propelled by powerful lasers, or even hypothetical fusion engines, would be necessary to cut down travel times. Ensuring crew or probe survival over these long durations also involves overcoming challenges in life support, shielding from cosmic radiation, and psychological well-being. Upon arrival, the environment encountered on a rogue planet would be unlike anything experienced in our solar system. Without a host star, the planet would be enveloped in perpetual darkness, its surface extremely cold unless geothermal or tidal heating provides warmth. The lack of solar energy means that any life-supporting processes would rely entirely on internal heat and chemical energy sources. Designing landing crafts, exploration tools, and scientific instruments capable of functioning in extreme cold and darkness is essential. Sensors specialized for infrared and neutrino detection would be critical for probing beneath icy crusts to locate subsurface oceans or geothermal hotspots. Autonomous or remotely operated submersibles might explore hidden liquid environments, searching for signs of life or geological activity. The surface may be cloaked in thick ice or dust, with atmospheres possibly rich in exotic gases. Robotic explorers must be equipped to analyze these alien chemistries and temperature extremes. Energy and communication pose further obstacles. A spacecraft must carry sufficient power, either generated from onboard nuclear reactors or harvested from limited ambient sources, to sustain operations for extended periods. Communication delays at interstellar distances mean that remote control is impractical. Autonomous decision-making and fault tolerance become critical for the mission's success. Yet the scientific and philosophical rewards of such a journey are staggering. A rogue planet offers a laboratory to study planetary formation and evolution in isolation, untainted by solar radiation. Investigating its geology, atmosphere, and potential biospheres would widen our understanding of life's versatility and the fundamental processes shaping planets. Moreover, a rogue planet probe or manned mission could reveal clues about the frequency and mechanism of planetary ejections, test theories of planetary cooling and heat retention, and possibly detect biomarkers indicating life in subsurface oceans. Such a mission would also foster international cooperation and technological innovation, driving advancements that ripple across space exploration and related fields. It challenges humanity's spirit of curiosity and resilience, inspiring new generations to imagine themselves as voyagers venturing into the darkest reaches of space. In planning this grand journey, ethical considerations emerge as well. How do we preserve pristine alien ecosystems? What responsibilities accompany contact with another world's environment? These questions intertwine scientific ambition with our broader sense of stewardship and cosmic humility. In sum, visiting a rogue planet entails an interstellar odyssey characterized by immense distances, technological challenges, and profound unknowns. Yet, it beckons as a gateway to exploring worlds beyond suns, revealing the richness of cosmic diversity and the potential for life in the universe's most solitary realms. With this vision in hand, we now reflect on the enduring legacy and frontiers that the study of rogue planets offers to planetary science and our understanding of the universe, charting a course for future discoveries and explorations. The study of rogue planets, those solitary worlds wandering the vast cosmic wilderness without a host star, has ushered in a transformative era in planetary science and broadened our understanding of the universe's complexity. Far from mere anomalies, rogue planets serve as living laboratories illuminating the profound dynamics of planetary formation, evolution, and galactic architecture. Their legacy lies not only in the insights they provide into the nature of planets themselves, but also in the frontiers they open for future research, technological innovation, and philosophical reflection about our place in the cosmos. At the foundation, rogue planets challenge the traditional paradigms that have long dominated planetary science. The classical view centered planetary existence around the gravitational influence and illumination of a star, forging a paradigm where habitability, detection, and formation were intrinsically linked to stellar presence. The identification and characterization of rogue planets upend this by demonstrating that planets can form, evolve, and even possibly harbor life independent of stars, expanding the definition of what constitutes a planetary environment. Studying rogue planets compels us to revisit and refine models of planetary system formation and dynamics. Their existence attests to the violent, chaotic, and complex processes within nascent planetary systems, processes involving gravitational interactions, ejections, and disruptions that can shuffle and scatter planets into lonely orbits or interstellar travel. This knowledge deepens our grasp of the diversity and instability inherent in planetary systems, emphasizing that the serene orbits of solar system planets are but one outcome among many possibilities. Moreover, rogue planets enrich our understanding of planetary demographics across the galaxy. If, as current research suggests, they may be as numerous as stars or more so, they represent a significant reservoir of baryonic matter and dynamic agents influencing galactic structure and evolution. Their study helps constrain models of planetary population synthesis and galactic formation history, bridging small-scale planetary science with large-scale astrophysics. From an astrobiological perspective, rogue planets push the boundaries of habitability, demonstrating that life's potential niches may extend far beyond the traditional habitable zones around stars. Research into their internal heat sources, subsurface oceans, and potential for harboring life in darkness challenges and expands the search for life in the universe to environments once considered utterly hostile. Technologically and methodologically, the endeavor to detect and analyze rogue planets has driven advances in observational astronomy, including refined microlensing techniques, infrared detector sensitivity, and data analysis methods utilizing artificial intelligence. These advances ripple outward, enhancing our capabilities to study faint and distant cosmic phenomena across disciplines. Philosophically, rogue planets invite reflection on the nature of existence and isolation in the universe. As lonely worlds without suns, they metaphorically and literally embody solitude amid the cosmic vastness, inspiring contemplation about the conditions for life, the diversity of planetary destinies, and humanity's own cosmic journey. Looking forward, the frontier lies in combining observational prowess with theoretical insight, mapping the rogue planet population in our galaxy, unraveling their origins in more detail, probing their internal dynamics, atmospheres, and possible biosignatures. Upcoming telescopes and missions promise unprecedented sensitivity to these faint wanderers, opening pathways to discoveries that may reshape our cosmic perspective once again. In essence, the study of rogue planets stands at the nexus of planetary science, astrobiology, and cosmology, enriching each field and inspiring visionary questions. These starless wanderers are not only the loneliest worlds, but also the harbingers of new paradigms and enduring mysteries in our quest to comprehend the universe's grand tapestry. With the legacy of their discovery well established and the frontiers ahead inviting exploration, we arrive at the continuous, unfolding journey, the ongoing search for the loneliest worlds, where each discovery deepens the cosmic story and expands the horizon of human understanding. The quest to find and understand rogue planets, the loneliest worlds adrift in the universe, remains one of the most compelling and challenging frontiers of modern astronomy. Despite decades of theoretical anticipation and progressively sophisticated observational campaigns, these starless wanderers largely remain ghosts in the cosmic darkness, elusive and mysterious. Yet, the ongoing search is a testament to human curiosity and ingenuity, a story of relentless pursuit, technological innovation, and the slowly forming mosaic of our galactic neighborhood. The foundation of this search lies in adeptly combining indirect detection methods like gravitational microlensing with infrared and astrometric observations. Microlensing surveys, including projects like OGLE and EMO, have cataloged thousands of transient events hinting at free-floating planetary masses. Still, many remain candidates requiring further confirmation, pushing astronomers to develop ever more sensitive instruments and algorithms. The instrumental advances on the horizon promise to revolutionize this quest. The Nancy Grace Roman Space Telescope, with its wide-field microlensing survey capability, will significantly increase the number of detected rogue planets across a wide mass range, including Earth-sized objects. Simultaneously, facilities like the Vera C. Rubin Observatory will systematically scan the sky to identify nearby, faint rogue planets through their motion against background stars, employing groundbreaking data analytics. Complementary spectroscopic and direct imaging observations by telescopes such as the James Webb Space Telescope and the upcoming extremely large telescopes will characterize rogue planet atmospheres and thermal emissions, offering unprecedented insights into their physical nature, histories, and potential for hosting life. Gaia's precise astrometry may detect the subtle gravitational influences of rogue planets passing near stars, highlighting an innovative avenue for discovery. The search is far more than a technological endeavor. It also requires developing refined theoretical models to predict rogue planet populations, ejection mechanisms, and their dynamical evolution within the galaxy. These models guide observational strategies, help interpret ambiguous data, and extend our understanding of planetary system formation and decay. Furthermore, the search has inspired interdisciplinary collaboration, drawing together experts in planetary science, astrophysics, astrobiology, and engineering to weave together observational data, simulations, and laboratory experiments exploring life's resilience in extreme environments. The discovery of rogue planets promises to deepen our grasp of planetary diversity, galactic dynamics, and life's possible niches beyond traditional star-bound worlds. Each new detection echoes not just a world discovered, but a testament to the universe's complexity and the endless scope of cosmic exploration. As our eyes and instruments become sharper and our theories more refined, we edge closer to revealing the secrets of these loneliest worlds. The journey continues, weaving together human creativity, technology, and the endless cosmic dance, inviting us all to look upwards with wonder and anticipation for what lies hidden in the darkness between the stars.